Welcome to the Learning Akka video course by Pact Publishing, authored by Salma Khatter. I am Tess Taylor, the voiceover artist for this course. Salma has an experience in cutting-edge technologies such as TypeSafe Stack. For the past 3 years, she has been using TypeSafe Stack in her daily life. She has also been actively involved in working on reactive and single-page applications. Our goal for this course is to get you well acquainted with Akka, to simplify some of the most important topics in Akka, such as routers, persistence, cluster, and Akka streams, and learn how we can implement them. By the end of this course, you will be familiar with Akka actors and the ways in which they communicate with each other, how to implement Akka cluster, Akka stream, and Akka HTTP, how to test your actors. Let's take a closer look at what we will cover in this course. First, we'll be introduced to the actor model and some important concepts such as concurrency, parallelism, asynchronous, and synchronous. Next, we will explore the actors in Akka through actor components, actor lifecycle, actor system, and what are the different supervision strategies. We will also cover the relationship between parent and child actors. And of course, we will create actors and talk to them. We'll play with different types of actors, such as router actor, finite state machine actor, and persistent actor. Then, we will work with Akka cluster, how actors join a cluster, how to log metrics about each node in the cluster, how to use the load balancer, cluster singleton, and cluster sharding. In the next section, we will talk about different styles to test actor business logic. We will test a basic actor, parent-child actors, finite state machine, and multi-node. Next, we will work with Akka streams. We will get introduced to stream terminologies and implement reactive tweets. We will also work with graph stream, stream I/O, and of course introduce how to test streams. We will then work with Akka HTTP. We will move ahead to see server-side and client-side APIs. We will implement symbol REST APIs and also test them. As we move ahead, we'll work around common actor patterns that are useful, elegant, and instructive, such as balancing workload across nodes, throttling messages, shutdown patterns, ordered termination, scheduling periodic messages. To follow along, the course assumes that you are familiar with the fundamentals of Scala, so that you have no issues understanding the examples shared throughout. Now that you have a roadmap for our journey in the course, let's get started. Welcome to the first section of this course. In this section, we will first take a look at understanding the actor model, then take a look at some concepts and terminologies to make sure we understand everything well, and finally, we'll create a Hello World app. Let's start with understanding the actor model. In this video, we will take a look at concurrent applications and why you need to design and write your application from the ground up with concurrency in mind. Then we will share a few problems we face with concurrency, and then, finally, we will introduce the actor model. In the past, processors doubled in speed about every 18 months, according to Moore's law. So, as a programmer, all you had to do was wait for the next generation of CPU so that your program would run faster. But now, things have changed. The processors are getting more cores, and each core is not getting faster as they did in the past. This means we need to use multiple cores, which in turn use multiple threads. So, now we should design our applications to use multiple cores and multiple threads, and one of the models that helps us to do this is the actor model. The predominant approach to concurrency today is that of shared mutable state. A large number of stateful objects whose states can be changed by multiple parts of your application, each running in their own thread. Typically, the code is interspersed with read or write locks to make sure that the state can only be changed in a controlled way, and prevent multiple threads from mutating it simultaneously. At the same time, we are trying hard not to lock too big a block of code, as this can drastically slow down the application. so we need to use multiple threads and also make sure our app state is saved and is correct at all times. This is very difficult with normal objects and operations that we use in our everyday implementations. We need objects that can handle non-blocking operations and can save this internal state from other objects. These objects are known as actors. An actor is a computational entity that, in response to a message it receives, can concurrently send a finite number of messages to other actors, create a finite number of new actors, designate the behavior to be used for the next message it receives. This means the actor was designed to communicate throw messages, and depending on the message, it can change its state and maybe change its behavior to handle a specific message. Let's take an example from our life to understand how actors work. Let's say you are an actor and your friend is another actor. You need to get some information about something random, so you send a message to your friend asking him to get this information for you. Your friend searches for this information and prepares the result to send it back to you. That is how actors work. To summarize, we know concurrent applications, the problems faced with concurrency, and the basics of an actor model using an analogy from our life. In the next video, we will talk about some concepts and terminologies such as concurrency, parallelism, asynchronous, and synchronous. Join me there. Welcome to the second video in this section. In the previous video, we talked about concurrent applications and the actor model. In this video, we will take a look at some concepts and terminologies to make sure we understand them as well as we know the difference between them. First, we will talk about concurrency versus parallelism. Next up, we will be asynchronous versus synchronous calls. Then we will talk about blocking and non-blocking of threads. And finally, we will talk about race condition. Let's begin then. Concurrency and parallelism are related concepts, but there are fundamental differences. Concurrency is when two tasks may start, run, and complete with overlapping time periods. It doesn't necessarily mean they'll both be running at the same time. For example, multitasking on a single core machine. Parallelism is when tasks literally run at the same time. For example, on a multi-core processor. So, simply put, concurrency is the means of splitting up work into chunks, which may or may not be executed in parallel, but parallelism is chunking of work to be executed in parallel. The second thing in this video is asynchronous and synchronous calls. A method call is synchronous if the caller cannot make progress until the method returns a value or throws an exception. On the other hand, an asynchronous call allows the caller to progress after a finite number of steps, and the completion of the method may be signaled via some additional mechanism. It might be a registered callback, a future, or a message. Actors are asynchronous by nature. An actor can progress after a message is sent without waiting for the actual delivery to happen. The next thing we'll look at is non-blocking and blocking. We talk about blocking if the delay of one thread can indefinitely delay some of the other threads. In contrast, non-blocking means that no thread will be able to indefinitely delay others. For example, if a thread writes a file on a disk and the operation takes ages as the disk access is slow, this thread will delay other threads and block them. But if the thread just signals that it wants to write something to the disk and registers, a callback will be executed once the write has succeeded. In this case, the thread doesn't delay other threads. The final concept we need to know is race condition. One kind of race condition arises when multiple threads have a shared mutable state. This means two threads try to change the shared state at the same time. Actors are safe from such race conditions as they receive messages one by one, and at the same time the actor processes one message. Hence, there can be no race condition inside the actor. Another kind of race condition arises when the application depends on ordered operations to be done correctly. For example, a client sending unordered packets P1 and P2 to a server. Imagine a scenario where the server receives P2 first and P1 later. If the messages contain no information about their sending order, it is impossible to determine from the server they were sent in a different order. Depending on the meaning of the packets, this can cause race conditions. This kind of race condition can happen with actors when actor A and actor B send messages to actor C at the same time. These two messages are racy because it is not deterministic which message gets delivered to actor C first. So, to summarize, we learned some concepts on concurrency, parallelism, asynchronous, synchronous, blocking and non-blocking, and finally, race condition. I hope I have simplified these concepts for you. In the next video, we will create an important app in Akka, the Hello World app. See you soon. Welcome to the final video of Section 1. Let's create Hello World. In the previous video, we talked about some concepts such as concurrency, parallelism, asynchronous, synchronous, blocking, non-blocking, and race conditions. In this video, we will take a look at how we can add Akka in our app and how we'll create a Hello World app. Let's begin then. To create the Hello World app, we need to define the greet message and the greeter actor that handles the greet message. Then, we'll create an instance from the greeter actor and finally send our greet message to our actor instance. The first thing we need to add is the Akka library on our library dependencies in the build.sbt file. Now we are ready to define the greet message and greeter actor. For this, we need to define our greet message. So let's define a case class, who2greet, which takes a single string parameter. Then we'll define the greeter actor. Let's define the class greeter that extends the actor trait, for which we need to define an implementation for the receive function. A receive function is a partial function that takes anything and returns a unit. As we have a single message, we'll have one case. When our actor receives the who2greet message, we want to print the hello message. Now, let's create an instance of greeter actor. In Akka, you can't create an instance of actor like an instance of normal class. We will create our instance using the theActorOf method in the actor system. We will learn more about this in the next section. First, let's create our actor system, and then we create an instance of greeter actor. The actor_of function takes two parameters: props, that is essential, and actor name, that is optional. If we don't provide the actor name, Akka will generate one for us, but most of the time, we'll provide a unique name for our actor. Now we have a running instance of the greeter actor, let's send the who2greet message to this instance. We will use tell to send our message. Don't worry, we'll go through the details in the next section. Now, let's run our app. There's our greeting message. Excellent! At the end of the video, we learned how to add Akka on our app, created our first app that contains greeter actor and who2greet message, and finally sent our message to our actor. This marks the end of Section 1. In this section, we introduce the actor model and the problems before the actor model. Next, we discuss some concepts such as concurrency, parallelism, asynchronous, synchronous, non-blocking, blocking, and race condition. And finally, we created the important app called Hello World app. In the next section, Playing with Actors, we will introduce actor components, actor lifecycle, actor system, and supervision strategies. Welcome to Section 2, Playing with Actors. In the previous section, we introduced the actor model and some important terminologies to get ourselves started. We ended the section by creating a Hello World app. In this section, we will take a look at the actor system and hierarchical structure for actors. Next, we'll delve into the actor component and actor lifecycle. We then move on to actor definition and creation with props. I know we created greeter actor in the previous section, but in this section, we will go deeper into the actor creation and recommended best practices. Then we will talk to actors. Finally, we'll discuss supervision and monitoring. Let's start our first video, Actor System and Hierarchical Structure. In this video, we will take a look at the actor system and hierarchical structure for actors defining the Akka system, and finally end with the Akka system component. Let's get rolling then. The actor is an object that encapsulates the state and behavior. The actors communicate by exchanging messages. You can think about the actor as a person. In the previous section, in the first video itself, we considered you and your friend as an example from real life. In this video, we have another example from our life to express the hierarchical structure of actors. Like in a software team, actors naturally form hierarchies. Let's express our life in our team. The project manager receives requirements from the project owner or a client. He applies some processes on it and distributes it over the development teams. Every team leader takes the requirements and splits it into smaller tasks and distributes them over to his entire team. Every member in the team takes up a task and completes it according to his responsibilities, and when he finishes it, he reports it to his leader. He gives the status as per whatever he has completed or hasn't completed because of some issues. In other words, every team member needs to complete a particular task, maybe do it himself or split it into smaller tasks, distribute them over to his team, and manage his team to complete it. Let's express this situation in the actor world. One actor, which is to oversee a certain function in the program, might want to split up its task into smaller, more manageable pieces. For this purpose, it starts child actors which it supervises, and if one actor does not have the means for dealing with a certain situation, it sends a corresponding failure message to its supervisor, asking for help. Now for the question of the hour. What's the actor system? The actor system is our root of the actor's structure. The actor system as a collaborating failure ensemble of actors is the natural unit for managing shared facilities such as scheduling services, configuration, and logging. Now, let's take an overview of the actor system components. The dead letter office is an actor, structurally no different from any other actor. Anytime a message is destined for an actor that either doesn't exist or is not running, it goes to the dead letter office. The user guardian actor is the parent of all actors we create from the actor system. For internal actors that Akka creates to assist you, there is a system guardian actor. It serves the same purpose as the user guardian actor, but for system actors. The scheduler is a part of the actor system responsible for scheduling things that may arise in the future. The event stream is the main event bus of each actor system. It is used to carry log messages and dead letters. You can also use it to publish messages across your entire actor system. Akka uses a new configuration system that's useful for configuring Akka and your application. You can access it from the actor system. The part of the actor system with which we've interacted mostly has been the user guardian. The user guardian is the parent for the actors we create from actor system, which watches and takes care of them. To summarize the concepts of this video, we have talked about actor system, its components, and the hierarchical structure for actors. See you in the next video, Actor Components and Lifecycle, where we will introduce how Akka uses several components that work together to deliver the actor experience. Welcome to the second video in Section 2, Actor Components and Lifecycle. In the previous video, we introduced the actor system and hierarchical structure for actors. In this video, we will take a look at actor components and how Akka uses several components that work together to deliver the actor experience. Then we'll take a closer look at the actor lifecycle. Let's start. The actor isn't just an actor class. Akka uses several components that work together. An actor for the outside world is like a black box. But when we open this box, we will find the following components. Actor. It is your instance which contains the state and behavior. Mailbox. It is the piece which connects the sender and the receiver. Each actor has exactly one mailbox to which all senders enqueue their messages. Dispatcher. It is the engine of the machine, so to speak. And the interface for this box is actor reference. Let's express how actors work to understand these components. When we send a greet message to greeter actor, we don't send the message to an actor instance, but we send it to actor ref, The actor ref is the only way to interact with the actor itself. Actor ref will then contact the dispatcher and use it to queue the message onto the actor's mailbox. The dispatcher will then put the mailbox into a thread, and when the mailbox executes, it will dequeue the messages and send it to actor's receive method for processing. The important thing is once the message has been put in the mailbox, the caller is free to do whatever he wishes. This means it does not block after passing in the message. We now need to know what happens to the actor from birth to death. An actor, like any other object, has a life cycle. We represent this life by this state diagram. When we create an actor by the actor of method, the actor system will construct our actor instance and execute the constructor method that calls pre-start in the actor world. Now the actor state is started, which means the actor is up and is able to process messages. The actor can receive a stop message or finish his work and shut down so that the actor state is stopped. This means that an actor will clean his resources and terminate. In another situation, when it processes a message and an exception is thrown, we have more than one choice, which we'll look at in more depth in the last video in this section: supervision and monitoring. The first choice, the actor will simply resume processing messages as if nothing extraordinary has happened. The second one, the actor will restart with a new actor instance. The third choice is the actor will stop. We will return to the actor lifecycle when we talk about supervision strategies, and we will implement callback hooks such as pre-start, pre-restart, post-stop, and post-restart. To summarize, we discussed actor components, and we now know that an actor isn't just the actor class, and Akka provides us with other components to work together to deliver the actor experience. Finally, we discussed the actor lifecycle, to which we will return to in supervision and monitoring video. See you in the next video, where we will start playing with actors by coding actors with real logic, not just printing the hello world message. Welcome to the third video in section 2, creating actor with props. In the previous video, we explored actor components and actor lifecycle. In this video, we will take a look at actor definition and creation. We'll touch up on props, and finally, we'll talk about recommended practices. Let's get started. As we saw from the previous section, an actor class is implemented by extending the actor class and implementing the receive method. But what's a props? Props is a configuration class to specify options for the creation of actors. Now it is time to get some coding under our belt. We need to define two actors, music player and music controller. Music player can handle two messages, stop music and start music, and music controller can handle two messages, play and stop. When music player receives the start music message, he will create an instance from music controller and send play message for him. So let's start with music controller. First we need to define messages. Let's use the best practices to define messages which the actor handled in the companion object for an actor. Also create a sealed trait that any message should extend it. Now, let's create the music controller class that extends the actor trait and defines our receive method. When it receives the play message, it prints out music started, and when it receives the stop message, it prints out music stopped. Now, let's create the music player actor. Let's define messages for the music player actor. First, we'll define the companion object for the music player actor and also define two case objects for our messages, stop music and start music. Then, let's complete our implementation and handle two messages. When it receives the stop music message, we will print out, I don't want to stop music. When it receives the start music message, it needs to create the music controller instance and send this message for it. Now, let's create a running instance from the music player actor. Of course, we should not forget to create our actor system. Let's express this line. The actor system requires the configuration for our actor to be able to create the actor environment. This configuration is the props class so that we can pass the props of the music player actor to the actor system. Next, we send the start music message to the music player actor. Now, let's run the app. There are our messages. Great! Our code is running. That's okay, but our code needs some enhancement. The first thing is the actor receives the block. It is a partial function. This means you need to provide a pattern match for all messages that it can accept, and if you want it to be able to handle unknown messages, then you need to have a default case. So let's go about defining the general case. The second thing is that declaring one actor within another is very dangerous and breaks actor encapsulation. Never pass an actor's this reference into props. Recommended practice here is defining the method props in the companion object for the actor that returns props for the actor. Now, let's run the app again to ensure that it's still running. Excellent! It works. In the next video, we will talk about how to send messages to the actor via ask and tell. See you! Welcome to the fourth video in section 2, Talking to an Actor. In the previous video, we created two actors, music player and music controller. In this video, we will take a look at the ways in which we can send a message to the actor, such as tell and ask, and take a look at their implementation. Let's begin. Messages are sent to an actor through one of the following methods. Tell, which is fire and forget. This means you send a message asynchronously and return immediately. In other words, you aren't interested in the result. Ask sends a message asynchronously and returns a future representing a possible reply. Let's express our use case that we will be implementing in this video to understand what's the difference between ask and tell. Imagine we are in the registration system and we want to implement the part that's responsible for adding users in the system. But we need to check before adding a new user to see whether he or she is blacklisted or not. Let's start by implementing three actors: recorder, storage, and checker. The recorder is the actor that is responsible for handling a new user message. When he receives a new user message, he will send a message to the checker to check whether this user is blacklisted or not. When the checker receives a check user message, he will check whether this user is in his list or not. If the user is in the blacklist, the checker will send a black user message to the recorder. And if the user isn't in the blacklist, the checker will send a white user to the recorder. When the recorder receives white user, he will send an add user message to storage. In our solution, the recorder sends two types of messages. A message for the checker to see if he is interested in the result, so this message will be asking, and another message is to storage in order to see if he is interested in the result, so this will be a tell. You can access the source code from this link. Let's start coding now. First, let's define a case class representing the user that contains the username and email. Then define our messages. New user, which contains the user instance. Check user message, which contains the user. And finally, the add user message, which also contains the user. Then, we need to define the checker response messages, black user and white user. Now, let's define a storage actor. This actor contains the user's list. When he receives an add user message, he adds a user in the user's list. Next, let's define the checker actor. This actor contains a blacklist. When he receives a check user message, he checks if this user is in the blacklist. And sends a black user message to the sender. And if the user isn't in the blacklist, he sends a white user message to the sender. The sender in this case is a method that returns the actor ref class that sends a message. Now, let's define the recorder actor. This actor handles the new user message. When he receives this message, he asks the checker about the new user. The ask method sends an asynchronous message and retains the future that will contain the result. We will map the result in case it is a white user. We will send an add user message to the storage via tell, as the recorder isn't interested in the result. Here is the object that extends the app. We will define the actor system and create our actors and send the new user for the recorder actor. Let's run the app now. Yeah, that's our printing message. Excellent. See you in the last video of Section 2, Supervision and Monitoring, where we will be taking a look at the relationship between parent and child actors. Welcome to the last video in Section 2, Supervision and Monitoring. In the previous video, we discussed sending a message to an actor via tell and ask. In this video, we will take a look at what's supervision, the supervision strategies in Akka, what's the monitoring, and finally, we will implement some actors to understand supervision and monitoring. Let's start. Supervision describes a dependency relationship between actors. The parent and child relationship. The parent is unique because it has created the child actor, so the parent is responsible for reacting when failures happened in its child. I think you remember this diagram from the second video, where we had described that we had 3 choices if an exception was thrown: resumed work, stopped, restarted. But we didn't discuss who was responsible to decide what's the better choice. The simplest and only answer is the parent for the actor. When the parent receives a signal failure from one of its children, depending on the nature of the work to be supervised and the nature of the failure, the parent has a choice of the following 4 options. Number 1. Resume the child, keeping its accumulated internal state. Number 2. Restart the child, clearing out its accumulated internal state. Number 3. Stop the child permanently. Number 4. Escalate the failure, thereby failing itself. This means I can't handle this failure, so I'll propagate this failure to my parent. Just note that supervision-related parent-child communication happens by special system messages that have their own mailboxes separated from the user messages. This implies that supervision-related events are not deterministically ordered relative to ordinary messages. In general, the user cannot influence the order of normal messages and failure notifications. Now, let's list down the supervision strategies that come with Akka. We have one-for-one strategy and one-for-all strategy. Simply put, in one-for-one strategy, the parent will apply his choice only on the failed child. On the other hand, for one-for-all strategy, the parent will apply his choice on all children. The default strategy is one-for-one strategy, and normally you should be using it. Now, let's check out what monitoring is used to tie one actor to another, so that it may react to the other actor's termination, in contrast to supervision, which reacts to failure. In other words, actor A monitors actor B, because actor A wants to receive a signal when actor B is terminated. Now, let's get down to business. Coding. We have 2 examples, supervision and monitoring. In the supervision example, we have Aphrodite and Hera as actors. Hera is the parent of Aphrodite. In Aphrodite, we implemented lifecycle hooks to understand what happens when an actor stops, resumes, and restarts. Let's add supervision strategy in Hera. We will override supervisor strategy. When he receives a failure signal with a resume exemption, he will resume his child. When he receives a failure signal with restart exception, he will restart his child. When he receives a failure signal with stop exception, he will stop his child. For any other failure, he will send this failure to his parent. Here, we will send resume the message to the hearer actor. Let's run to show the result. Now, let's send a restart message and run. Yeah, these are our messages. Aphrodite, pre-start hook. Hearer, received restart. And this is the exception thrown, and then hearer restarts Aphrodite. Aphrodite, pre-restart hook. Aphrodite, post-stop. Aphrodite, post-restart hook. Aphrodite, pre-start hook. Aphrodite, post-stop. Now, let's try to stop the message. Yeah, that's the result we expected. Excellent. Now, the final thing for this video is an example on monitoring. We have a simple example, just two actors here, Ares and Athena. The Ares actor takes a reference to the Athena actor and will monitor it by invoking the watch method on restart. When he receives a terminated signal, he will stop himself. Now we have the Athena actor. He is a simple actor. When he receives just a message, he prints this message and stops himself. Let's run our app. Awesome! That is the expected result. Good job! We have now reached the end of section 2. Take a look at what we've covered. We saw the actor system and its components. We then discussed the actor components and lifecycle. We started coding some actors to understand the actor definition and their creation. We sent messages to the actor via tell and ask, supervision and monitoring. See you in the next section, working with Akka basic tools, where we will implement router actor, stateful actor, and change the actor behavior at runtime. Welcome to section 3, working with Akka basic tools. In the previous section, you learned the basic actor concepts in Akka. In this section, we will take a look at the basic tools in Akka, such as actor ref versus actor path versus actor selection, routing, replace actor behavior via become, unbecome, replace actor behavior via FSM. Let's start our first video actor ref versus actor path versus actor selection. In this video, we will discuss what's the difference between actor ref, actor path, and actor selection. In the previous section, when we discussed actor components, we said that the actor ref is the interface of the actor instance. Actor ref is a reference for a single actor. It is created when an actor instance is created and is pointed to this instance. When the actor restarts, the instance still points to the same actor ref, but when the actor shuts down, the actor reference will point to a dead letter. And when you create a new instance, Akka will create a new actor reference. This means actor references don't change during the actor lifecycle. We know actors are created in a strictly hierarchical fashion. If we are thinking about an actor's tree like a file system and want to get a path for actor B, it's a /user/A/B. This is a path for an actor. Actor path is a location of the actor on the actor system tree. It's a sequence of actor names given by recursively following the supervision links between a child and parent, down towards the roots of the actor system. The difference between an actor path and actor ref is that the actor path represents a name of the actor, which means you can create the actor, terminate it, and then create a new actor with the same path. The newly created actor is a new instance of the actor, which means it has a different actor reference. Actor selection is another representation of the actor like actor reference. You can send messages to an actor via actor selection, like actor ref. But the main difference between them is that the actor selection is created from the actor path or actor name. This means that the actor selection stays valid, even when an actor dies and another instance is created. So you can't watch the actor selection like actor reference because actor selection doesn't represent a single instance, it represents a path. Now let's play with an actor reference and actor selection. We have a counter actor that handles two messages, increment and decrement, and has a count variable. Now let's create an instance from a counter. Then let's print an actor reference for our instance. After that, let's create an actor selection. We will use the actor selection method that takes a path or name. We will give it our actor name and print the actor selection for our actor. Then, let's kill our counter instance and create a new one, and a new actor selection. We'll print a new actor reference and actor selection. Let's run! Yeah, it's not the same actor reference, but it's the same actor selection. We said we can't watch the actor selection, but what if we don't have an actor reference, and we know just a name for the actor? How can we watch it? It's simple. By default, every actor can handle a message called identify and replay to this message with the actor reference. So you can easily convert actor selection to actor reference and avoid using actor selection. So let's create a watcher actor that will have a selection value for the counter actor. We will send an identify message for this selection. An identify message contains the message ID that will return a response. On the receive method, we will handle the response of identify. Actor identify contains a correlated ID, which is the message ID, and an optional value for actor ref. When the actor is live, it will have some value for actor ref, and when the actor does not exist, the value will be none. Now, let's create two instance forms, counter and watcher. Let's run. Great, that's the actor reference for the current running counter instance. To summarize, we discussed the difference between actor reference, actor path, and actor selection. See you in the next video to create and play with routing. Welcome to the second video in Section 3, Sending Messages via Routers. In the previous video, we discussed the difference between actor reference, actor path, and actor selection. In this video, we will take a look at how to implement the router actor based on our current knowledge of Akka and router types. We will then implement some routing strategies that come with Akka, such as random router. And finally, we will introduce other routing strategies in Akka. Let's start coding then. First, let's take a look at the worker actor. This actor handles only work messages. Now let's think about the implementation of the router actor. This actor should contain a list of workers, known as its routees. So let's add pre-start method and create 5 instances. When a router receives a work message, it selects the routee and forwards the message for it. It will select a random actor from routees. Forward message means that the original sender reference is maintained, even though the message is going through a mediator, like a router. In the app project, we create the router instance and send to it 3 messages. Let's run the app and check our printing messages. Excellent! Our router is working. In our implementation, router actor is the parent for routees. This is called pool. We have another type of router, which is a group. That means routees are created externally to the router, and the router sends messages to the specified path using an actor selection. Now, let's implement group router. The group router takes the routees list on the constructor, receives implementations such as router pool, except for instances where we need to use actor selection to forward the message to it. In app object, we created 5 worker instances. Then we created the list which contains paths for actor instances. Our instances were created under our system actor, so the path for worker 1, for example, will be /user/w1. Then we create the router group instance. Let's run and check our printing messages. Good. Our implementation is good, but this implementation will produce a bottleneck in our app. So Akka provides specific implementation for router actor and comes with several useful routing strategies right out of the box. In Akka, we can define the router actor in configuration or in the code. Let's start implementing random router. First, we implement random pool in a configuration. In a configuration file, we add this configuration. Random router pool is the name of the actor. And this contains two variables, router type and number of instances. In the app object, we will create a router instance instead of props. We will use fromconfig.props that takes props of routee actor. Let's send 4 messages to the router. Now, let's run the app and check the printing messages. Excellent! Let's create a random group router in the code. Like the previous router group, we'll create 3 workers and define a path list. To define the router, we will use the actor_of method that takes props for the random group router and sends 4 messages to the router. Let's run the app and check printing messages. Excellent! I think now the definition of the router is a simple task. Let's quickly check out the other routing strategies in Akka. Round robin. Routes in a round robin fashion to its routees, and you can check an example in our source code. Balancing. A router that will try to redistribute work from busy routees to idle routees. All routees share the same mailbox, which means all routees will be on the same physical machine because they physically share the same mailbox. Smallest mailbox. Forwards the message to routees with the fewest messages in the mailbox. Broadcast. Forwards the message to all its routees. Scatter, gather, first completed. Will send the message to all its routes, then waits for the first reply it gets back. This result will be sent back to the original sender. Other replies are discarded. Consistent hashing uses consistent hashing to select a routee. Tail chopping is like scatter-gather, but sends a message to one routee, randomly picked, and then after a small delay, sends the message to the second one, and so on. It allows sending the same work to more workers if it seems as if the first one is not going to respond in time, and therefore, one can get way better latencies on responses sometimes. To summarize, we discussed routing strategies in Akka, and we implemented random router. You learn more about routing right here. See you in the next video. Replace actor behavior via become, unbecome. Join me there. Welcome to the 3rd video in section 3. Replace actor behavior via become, unbecome. In the previous video, we implemented the router actor and introduced router strategies in Akka. In this video, we will take a look at how to change actor behavior at runtime by become and unbecome, and we will introduce stash messages. Let's start! In this video, we will implement user storage actor. This actor should represent database operations for the user model. Our actor should be able to connect to the database, disconnect from the database, and perform CRUD operations. Let's start coding then. Here is the definition of the user. It's a simple representation. User contains username and email. And here we have the representation of database operations. First, let's define the messages. We have connect message. So let's go ahead and add a case object connect. Add another object to represent a disconnect message. And finally, CRUD messages. So let's add a case class that represents database operation, which takes database operation and an optional user. Now, let's start thinking about the implementation of user storage. Our actor has 2 states when connected to the database and disconnected from the database. Every state for an actor is represented by the receive function, so let's add a connected and disconnected function. In the disconnected function that represents the disconnected state, we need to handle the connect message. So let's add a connect case. For simplifying, we just print a message. After the actor connects to the database, we need to change the actor behavior to the connected state. We will invoke the context.become function. .become takes a receive type. Receive type is partial function that takes any and returns unit. In the connected state, we need to handle disconnect and operation messages. So let's add two cases, one for disconnect message, which invokes the context.unbecome function that resets the latest become. That means the actor state changed to the disconnected state. And in another case for operation message, we just print a message. We defined two receive functions, but we still didn't define the default behavior, or state for our actor. I think our actor should start with the disconnected state. In the app object, let's define an instance from the user storage and send a connect message, and then create a message, and finally disconnect. Let's run the app. Great, it's working. But what happens if we try to send a create message before a connect message? Let's try it. Yeah, our actor doesn't handle the create message because it receives this message on the disconnected state, and this message handles the connected state. Let's fix it. We will fix this issue by using the stash trait. The stash trait enables an actor to temporarily stash away messages that cannot or should not be handled using the actor's current behavior. So we need to add a general case on disconnected function. If we receive any other messages, we will invoke the stash function, which adds the current message to the actor's stash. Lastly, we need to invoke the unstash_all function before we invoke the become function. Unstash enqueues messages from the stash to the actor's mailbox. The stashed messages can be processed in the same order as they have been received originally. Now let's run the app and check. There's a printing message for the create operation. Excellent! At the end of the video, we've seen the change in the actor behavior at runtime by the first way, become and unbecome. And of course, you can check the become/unbecome documentation here. See you in the next video with the second way to change the actor behavior. Welcome to the final video in section 3. Replace actor behavior via finite state machine. In the previous video, we introduced how to change actor behavior at runtime using become and unbecome. In this video, we will continue to see how we can change an actor's behavior at runtime. Here, we will take a look at an overview on FSM. Implement user storage we saw in the previous video with the help of FSM. Let's get started then. A finite state machine can be described as a set of relations of this form. If we are in state S and the event E occurs, we should perform the actions A and make a transition to the state S-. Now, let's take a look at the skeleton for an FSM actor. The first thing we need to do is declare the FSM actor that is extending the FSM trait, which inherits directly from the actor trait. The FSM trait takes two type parameters. The super type of all state names, usually a sealed trait with case objects extending it. The type of the state data that is tracked by the FSM module itself. In the body of the actor, we use a DSL to define a state machine. Start with is used to define the initial state and initial data, and there is one declaration per state. Finally, we will use initialize, which performs the transition into the initial state. Now let's get to the thinking part of it and see how we can implement user storage actor in the FSM form. Here are the same messages that we defined in the previous video. Let's define our state and data as well. we have two states, connected and disconnected. Our simple actor doesn't have any data to represent the internal actor state, so we add a case object for empty data. Now let's start implementing user storage FSM actor that extends the FSM trait and stash trait. We will implement the FSM actor in 3 steps. Number 1. First, we will define the start with function. In our actor, we start with the disconnected state and empty data. Number 2. Then we define our states. We have 2 states, so we have 2 definitions for when. The first one is when in the disconnected state. In this state, we will handle the connected message. The FSM actor doesn't receive messages, it receives events. We handle every event on the state function. A state function is a partial function that takes an event and returns its state. The event contains the message and the FSM actor. So when we receive an event that contains the connect message, we will add the same printing message from our previous video, and to return its state, we will use the goTo function, which takes the state, and uses the function that takes data. If we receive any event that contains any other messages, we should stash this message and, of course, stay in this state. Don't forget to add the unstash all message before going to the connected state. The other definition of when for the connected state is that our logic doesn't differ from the previous video, but in the FSM style. Number 3. The final step in implementing the FSM actor is invoking the initialize function. Here in the app object, we have a similar definition, sending the same messages from the previous video. So let's run the app. Great! It's working as the previous implementation. That's it for replace actor behavior. It's considered a best practice to use become and unbecome when you have 2 states, and if you have more than 2 states, it's preferred to use FSM. Another feature on FSM is for max. You can use it if you want to stay on the state for a specific period. You can check all things about FSM from the Akka documentation at this URL. And of course, you are the best person to determine the implementation that is perfect for your use case. At the end of section 3, we discussed the actor reference, actor path, and actor selection. We implemented the actor router and expressed the different strategies for the router on Akka. Finally, we discussed how to replace actor behavior via become, unbecome, and FSM. Join me in the next section, where we will introduce Akka Persistence. See you soon! Welcome to section 4, Akka Persistence. In the previous section, we discussed the difference between actor reference, actor path, and actor selection. We also introduced routing in Akka and how to replace actor behavior via become, unbecome, and FSM. Now let's start our next topic. In this section, we will take a look at overview on Akka Persistence and architecture. We will then implement a persistent actor and play with it. After that, we will look at persistent FSM. And finally, we will introduce Persistence Query, which is a new experimental module in Akka 2.4. Let's start with the introduction to Akka Persistence. In this video, we will take a look at what's a persistent actor, and what's the difference between a normal actor and a persistent actor. Then we will discuss the architecture of Akka Persistence. Let's start. Let's imagine we have an actor that contains a counter variable which increments after receiving a message. But if this actor crashes, we will lose the internal state. There are many cases where we need to retain the internal state as well. We need actors that can persist the internal state. When the actor crashes for some reason, we need to make sure his state is stored at a safe place, such as a database or a file. And after the actor restarts, it can read the last persisted state and start from there. Akka uses a very similar idea in Akka Persistence. The key concept behind Akka Persistence is that only the changes to an actor's internal state are persisted, but never its current state directly. This means that we don't store the internal state, but we store events from which the internal state can be recovered. The basic idea behind Akka Persistence is quite simple. A persistent actor receives a new message that calls a command which is first validated if it can be applied to the current state. If validation succeeds, events are generated from the command, representing the effect of the command. These events are then persisted and, after successful persistence, used to change the actor's state. When the persistent actor needs to be recovered, only the persisted events are replayed, for which we know they can be successfully applied. Now, let's introduce the architecture of Akka Persistence. Persistent actor. This is a persistent stateful actor. It can persist events to a journal and can react to them in a thread-safe manner. It can also be used to implement both the command and the event-sourced actors. When such an actor is started or restarted, journaled messages are replayed to that actor so that it can recover its internal state from these messages. Persistent view. It is a persistent stateful actor that receives journaled messages that have been written by another persistent actor. A view itself does not journal new messages. It instead updates the internal state only from a persistent actor's replicated message stream. This is deprecated from Akka 2.4, and we should use persistence query instead. We will discuss persistence query in detail in the last video of this section. Async write journal. A journal that stores a sequence of events sent to a persistent actor. An application can control which messages are journaled and which are received by the persistent actor without being journaled. The storage backend of the journal is pluggable. The default journal storage plugin writes to the local file system. And of course, this is not for production. For production, Akka recommends Cassandra or JDBC backend driver. Snapshot store. A snapshot store persists snapshots of a persistent actor. Snapshots are used for optimizing recovery times. The storage backend of a snapshot store is pluggable. The default snapshot storage plugin writes to a local file system. You can check the full documentation for persistence from here. And this is a link for Cassandra journal. And this one is for JDBC. Excellent! Now that we have a basic idea of Akka Persistence and its architecture, we will quickly move on to the next video where we'll implement a simple persistent actor. Welcome to the second video of Section 4, Creating Persistent Actors. In the previous video, we introduced Akka Persistence and discussed the persistence architecture. In this video, we will implement a persistent actor. So let's get started with it. We want to implement a counter actor that handles two operations, increment and decrement. From the previous video, we know that a persistent actor handles two types of messages, commands and events. Commands represent operations from the outside world, and on the other hand, events represent stored operations from the journal. So let's define our operations. Let's add sealed trait for an operation which contains a number of variables. Then we add a case class for the increment operation, and another one for the decrement operation. Now, let's define command and event. We add a case class for command, which takes an operation as an argument, and another one for event. The last thing we need to define before starting the persistence actor definition is the case class representing our actor state, which contains a count variable. Now we are ready to start the definition of a persistent actor. To define a persistent actor, you should extend the persistent actor trait. Once you extend a persistent actor, you must define the implementation for three functions: persistence ID, receive recover, and receive command. Every message in the journal needs an identifier for his persistent entity. This identifier should be defined on the persistence ID function. And you should know that there must be exactly one persistence actor with persistence ID running at the same time, and the persistence ID should be unique. The persistent actor has two states, recovering mood and normal mood. For this reason, we have two receive functions, the receive recover function for recovering mood and receive command for normal mood. And your assumption is right. A persistence actor starts with recovering mood. So let's start with our implementation. First, let's add the identifier for our counter actor. Second, let's define receive recovering. It defines how a state is updated during recovery by handling event and snapshot offer messages, if snapshots were made for this actor. So let's define a function to update state, which takes the event as an argument and returns a unit. And for each case, we will update the current state. Let's return to receive recovering. We have two cases here. When receiving the event from the journal, we should update our state. And when receiving a snapshot offer message, we should take our state from the snapshot. The last thing we need to define is receive command. From the previous video, we know that the persistent actor, when receiving the command, it checks if the command can apply on the current state, or not, then generates the event from the command and persists it. So in our case, when receiving a command, we will generate an event and persist it. The persist method takes two arguments, the event that will persist on the journal and a handler which is called on successful persistence. So if the event is successfully persisted, we will update our state. Now, let's add an extra case for printing our current state to understanding. Here is our app object. We defined the system actor and an instance of our counter actor and send some messages. Let's run our app. Great, it's working. But what happens if we run our app again? Let's try. Yeah, our actor starts from the previous state, not from a clean state. Now this actor is a persistent actor. See you in the next video where we will play with the persistent actor. We will show how to take a snapshot and deal more with recovery. Welcome to the third video of Section 4, Playing with a Persistent Actor. In the previous video, we implemented a persistent actor called counter. In this video, we will take a deeper look at how a persistent actor persists events and how it can handle failure. Then we will talk more about recovery mode. And finally, we will discuss how to take a snapshot for our counter actor. Let's start. In the previous video, we implemented the receive function as seen on the screen. When a command is received, we print a message and then call the persist method. The persist method asynchronously persists events and takes a sequence of events and handlers that will be called when persistence succeeds. It is guaranteed that no new command will be received by a persistent actor between the call to the persist method and the execution of its handler. This is achieved by stashing new commands and unstashing them when an event is persisted and handled. That means a persistent actor doesn't receive a new command until the event was persisted and handled. But we have another version from persist called persist async, which is like persist, except that the persistent actor can receive a new command after a call to persist async. So if you don't want to execute a new command after the effect of the current command, you should use persist async. It all depends on your logic. Another thing though, what happens if the persist event fails? When persist fails, onPersist failure will be invoked. By default, it logs the errors and the actor is always stopped after this method has been invoked. In this case, the event may or may not have been saved, depending on the type of the failure. Let's move to recovery. We already know that a persistent actor starts on recovery mode, and a new message sent to the persistent actor during recovery does not interface with the replayed messages. They are cached and received by a persistent actor after the recovery phase is completed. This can be disabled by returning recovery.none in the recovery method of a persistent actor. Let's try this. We'll run our example from the previous video. Yeah, our persistent actor replayed messages from the journal. Now, let's override the recovery method. Let's run it again. Yeah, our persistent actor doesn't replay the messages from the journal. Great. If you need any initialization done after recovery completes, we can handle the recovery completed message on the receive recover method. Let's add it. First, let's enable recovery again. Now, let's add a new case for the recovery completed message so that we can just print a message. Let's run. Excellent, here is our message. Now, let's take a snapshot when our state contains a number which is a multiple of 5. Let's add a method called takeSnapshot. This method will check if count is a multiple of 5. If it is, the method will take a snapshot. We will use saveSnapshot method which takes a state. If saving of a snapshot succeeds, the persistence actor will receive a saveSnapshot success message, otherwise a saveSnapshot failure message. So let's add a saveSnapshot success message on the receive command method, and we will just print a message. And add a case for failure and print a message. Cool! Add takeSnapshot function in update state. Let's run this. Awesome! Our snapshot was saved. Let's run again. Excellent! Persistent actor receives snapshot offer on recovery mode. We're at the end of the video. We have completed our persistent actor. We handled snapshots and added recovery complete handler. We also discussed persist and persist async. We then disabled recovery on the persistent actor. See you in the next video to implement the persistent actor in FSM style. Welcome to the 4th video in section 4, Persistent FSM. In the previous video, we dived deep into the process of working with persistent actors. In this video, we will implement the replacement of persistent actor behavior via FSM. Let's start! We will implement an account actor that's responsible for managing an account for a specific user. This actor has 2 states, empty when the balance is 0 and active when the balance is greater than 0. Let's start the implementation. The FSM actor needs a definition for states and data. So let's define states. We have 2 states. We will define a sealed trait for our states which extends FSM state. We will add a case class to represent the empty state that extends state. And we also extend FSM state, so we need to implement an identifier method that defines the string represent state. Let's add another case class for active state. Now let's define our data. The data will represent the balance for account. So let's add a sealed trait for data that contains the amount value. We have 0 balance as a case object, and balance case class that represents balance. Now we've defined states and data for the FSM actor. But for implementing the persistent FSM, we need to define events and commands as persistent. Let's change events to domain events, because we already have event on FSM. First, let's define our domain events. Think about persist event on this actor. Yeah, it's a transaction. This represents the transaction amount and type, if it's a credit or debit, and if we have accepted a transaction or rejected it. Let's define a sealed trait called domain event. We have 2 events here, accepted transaction that contains the amount and type, and rejected transaction that contains amount, type, and reason. Let's define transaction types which will be credit and debit. Now, let's define our command. I think we have one operation that contains an amount and a transaction type. Now we have defined things that are needed for FSM actor and things that represent the operation and events for a persistent actor. We are now ready to start implementing the persistent FSM actor. Our actor will extend persistent FSM trait of state, data, and domain event. We need to override 3 methods before we start to implement our states handler: persistence ID, apply event, and domain event class tag. We know what's the persistence ID, right? It's a unique identifier for a persistent actor. Let's move to the second method. It's called apply event. I think its name is descriptive. If you remember in the last video when we implemented the persistence actor, we defined the method update state, and we called this method after persist event, and when we replayed the event from the journal. Apply event is like that method. The apply event method takes an event and the current data and returns its data. Let's start defining the logic for this method. When the case event accepts transaction with credit, we will calculate the new amount, print it, and then create a new balance. When the case event accepts a transaction with debit, we will calculate a new amount and return the new balance. When the case event rejects transaction, we will print a message with a reason and then return the current data. Let's move to third method, domain event class tag. I think its name is descriptive again. You need to return a class tag for your domain events. Now we will start defining our state handlers. Our actor will start with an empty state and zero balance data. We've got two states. Let's start defining them. When we are in the empty state. In the cases where we receive an operation with credit, we will go to an active state and apply the accepted transaction event with amount and credit transaction type. In case we receive an operation with debit, we will stay in the current state and apply rejected transaction, and the reason will be balance is 0. Now, let's define what will happen when we are in the active state. In case we receive an operation with credit, we will stay and apply accepted transaction. In case we receive an operation with debit, first we'll calculate a new balance and then check. If the new balance is greater than 0, it's OK. We will stay and apply accepted transaction. If it's equal to 0, go to an empty state and apply accepted transaction. If it's less than 0, we will stay but apply rejected transaction. Here we created an app object that contains an actor system and our account actor. Also, it sends two test operations to the account actor. Let's run the app. Yeah, our actor is working. Let's run it again. Excellent. It is replaying the events from the journal and then processing new messages. That's the end of this video. We have implemented the persistent actor in FSM style and used the experimental new feature on persistence, Persistence FSM. In the next video, we will explain another experimental module called Persistence Query. See you! Welcome to the last video of Section 4, Persistence Query. In the previous video, we've discussed Persistence FSM and implemented Account Actor as a persistent and FSM actor. In this video, we will take a look at CQRS pattern and what is the difference between it and the CRUD system. Then we will discuss Persistence Query. Finally, we will implement the view to read account transaction. First, let's express the CQRS pattern quickly. CQRS stands for Command Query Responsibility Segregation. The main idea behind CQRS is the separation between read and write operations. This mainly separates CQRS from the CRUD system, which handles the read and write operations in one place, whereas CQRS has two models. One of them is responsible for read operations, and another one is responsible for write operations. Now, let's start working with Persistence Query. The most typical use case of Persistence Query is implementing the read side in CQRS. Assume that our persistent actor has a write side which handles write commands and persists them on the journal. So when we start implementing the read side, we'll need something like a persistence query, which can read the persistent events from a journal. Akka Persistence Query itself is not directly the query side of an application. However, it can help to migrate data from the write side to the query side database. This means a persistence query is not your query logic for your application. It gives you access to read the persist events from the journal. Akka Persistence Query doesn't provide actual implementations for reading the journal. It defines a number of predefined query types for the most common query scenarios that most journals are likely to implement. However, they are not required to, which means you should check queries that are supported on your journal plugin. Let's check out some predefined queries. All Persistence IDs type is designed to allow user to subscribe to a stream of all Persistence IDs in the system. This means you can read all persist events in the system. Current persistent IDs is designed to read the current persist events and any new event you haven't received. Events by persistence ID is equivalent to replying a persistent actor. This means you can read events from a specific persistent actor and keep watching it. Current events by persistence ID reads the current events on the journal. Event by tag allows querying events regardless of which persistence ID they are associated with. The goal of this query is to allow querying for all events which are tagged with a specific tag. Current event by tag queries the current events. Now, let's implement a quick example. We will implement the view for our previous persistent actor. Let's read a persist event from our account handler persistent actor. I know the code is not familiar currently, but trust me, we will discuss all these lines when we cover Akka streams. First, we'll define our read journal, and we will use level DB read journal. Now, let's read our events. We will use events by persistence ID query that takes persistence ID for our actor. Finally, we'll print our events. Let's run this. Great! These are our events. You can check persistence query documentation from here, and persistence query level DB from here. We've reached the end of this section, where we discussed what Akka Persistence is and how we can implement a persistent actor. We played with recovery and snapshots on the persistence actor. Next, we mixed persistent actor with FSM to replace the actor behavior. And finally, we implemented a new experimental feature of Akka 2.4, persistence query. See you in the next section, on the next stopover in our trip with Akka Cluster. Welcome to Section 5, Working with Akka Cluster. In the previous section, we worked with Akka Persistence. We discussed Akka Persistence architecture and implemented a persistent actor. Then we implemented persistence FSM, and finally, discussed persistence query. In this section, we will work with other features in Akka, such as Akka Remote and Akka Cluster. First, we will introduce Akka Remoting and implement a remote actor. Then we will introduce Akka Cluster and implement some concepts on it such as load balancer, cluster sharding, and cluster singleton. Let's start with Akka Remoting in this first video. In this video, we will take a look at Introduction to Akka Remoting, preparing your actor system for Akka Remoting, starting a remote actor. Let's get started. In all the previous sections until now, we have worked on examples that have one actor system running on a local machine. But in real life, your application will pertain to parts, and every part may run on a different node. Everything in Akka is designed to work in a distributed setting, and the Akka team has done a great job of protecting the application from all the complexity that revolves around the remoting system. Now, let's define Akka Remoting. Akka Remoting is a communication module to connect actor systems in a peer-to-peer fashion, and it is the foundation for Akka clustering. In a production setting, it is recommended to rely on Akka Cluster directly instead of remoting. However, let's see how it works before we jump to the cluster. Let's start playing with Akka Remoting. Akka Remoting, like Akka Persistence, is a separate dependency, so we should be adding this dependency in our application. Now, to enable Akka Remoting, we should update our application.conf file. We should at least add these 4 things in our configuration. First, we should change the provider from akka.actor.localActor.ref_provider to akka.remote.remoteActor.ref_provider. Second, we add a TCP on the enabled transports list. Third, we define a hostname. Let's say it's our local host. And finally, we define a port. Let's say it is 2552. Each actor system needs to have either a unique port if shared on the same host, or they can use the same port if started on multiple nodes in a cluster. Now our application is ready. Great! Here is a worker actor that handles work messages, and when it receives a work message, it just prints that message. Now, let's create our actor system using our configuration. In the member service object, we will load our configuration and then create our system. Then, let's create an instance of the worker actor. This code is similar to the code from the previous sections, but the only difference is that this actor system is a remote actor system. Now, let's run this actor system. Great! Our actor system is running, and here we have the path for our worker actor. We have two types of remote interactions, lookup and creations. Lookup is used to look up an actor on a remote node with actor selection. Creation is used to create an actor on a remote node with actor of. Let's start with the lookup example. First, we'll add the configuration for member service lookup actor system. It is similar to our previous configuration, but we will change the port. Now, in the member service lookup object, we need to start our actor system. First, we need to read our configuration. Then, we need to send the message to the worker actor in another actor system. We will use the actor selection method. The pattern of remote actors path like this, it's like a path for normal actor, but we provide the remote system, host, and port. So let's add the actor selection for the worker. Then let's send a message for the selection actor. Now, let's run the member services lookup actor system. Now, let's check the first terminal. Yeah, the worker actor receives our message. Excellent! Now, let's try another remote interaction. First, let's add our configuration. In this example, we will add some extra configuration to describe the deployment for the remote worker service. Here is the creation of member service creation. It is our new actor system. Now, we will create a remote worker service actor using actor of, like any normal creation, and then send a message to it. Now, let's run the third actor system. Yeah, there is our message. Let's check our terminal for the first actor. Yeah, our worker actor received our message. Awesome, well done. You can check full documentation for Akka remoting from here. In the next video in this section, we will be introduced to Akka cluster, and we will implement a simple cluster. Welcome to the second video in section 5. Building a cluster. In the previous video, we introduced Akka remoting and implemented two types of remoting interactions, which are creation and lookup. In this video, we will take a look at Introduction to Akka cluster. Then we will start to build our cluster. Let's start. Akka cluster provides a fault-tolerant, decentralized, peer-to-peer based cluster membership service with no single point of failure or bottleneck. It does this using the gossip protocol and a built-in failure detector. Let's define some terms to make sure we were on the same page. Node is a logical member of a cluster. There could be multiple nodes on a physical machine. It is defined by a host name, :port, :UID tuple. UID is not user visible most of the time. It is used by Akka internally to identify whether it's the same system or a system on the same node and port, that ISA restarted the system. Next is cluster. It is a set of nodes joined together through the cluster membership protocol. The cluster assigns a special leader role to one of the nodes in the cluster. It will manage cluster convergence, such as down or up events. However, it is not an SPOF, as it is fine if this node fails. Another one would take over immediately. It manages. Seed node is a scan that can be configured as the contact points for new nodes joining the cluster. If you want to join a cluster dynamically via code, you can do so as well. Now, let's discuss the membership lifecycle. The node begins with the joining state. Once all nodes have seen that the new node is joining through gossip protocol, the leader will set a node in up. If the node leaving the cluster is safe, it switches to the leaving state. Once the leader sees the node in the leaving state, the leader will set a node in the existing state. Once all nodes see the existing state, the leader will remove the node from the cluster and mark it as removed. If something abnormal happens on the node, it is set to unreachable until the leader decides to mark them down. This can happen only when auto-downing is enabled, or Akka split brain is used or an operator or node invokes the down command explicitly. Now, let's move to our example in this video. We need to create this system where we have front-end and back-end nodes. Each node represents an actor system. The front-end node receives messages and delegates it to one of the registered back-ends. Now, let's build our cluster. The first thing we should do is add the Akka cluster jar in our project dependencies. Let's define the cluster configuration. We will configure the cluster to host nodes of two different roles, front-end and back-end. The role of node is to describe the node functionality. Not all nodes of the cluster need to perform the same function. For example, your cluster may consist of 4 nodes. 2 nodes are responsible for handling front-end functions, and 2 nodes are responsible for managing the data. We will use the remote configuration and add cluster configuration that contains roles and seed nodes. We will add both nodes as seed nodes. This is not strictly a requirement, but is the simplest way to get started for our example. Now, let's start with the back-end. Here is a normal actor that handles adding the add message. Let's add some logic for the cluster. When the back-end joins the cluster, the back-end needs to detect new, potential, front-end nodes and send them a registration message so that they know that they can use the back-end. So let's define a cluster from the context, .system. We need to subscribe to the cluster event. The pre-start, we will subscribe on the member up event. And in the post-stop, we'll unsubscribe. Next, we need to handle this event when we receive the member up message. We need to check if this member is a front-end or not. If it is the front-end, we will send a back-end register message to this member. And here is the initiating method that creates the actor system and back-end instance, which take the port for creating node. Now, let's move to front-end. In the front-end actor, we will add the back-end's variable. The front-end will handle the add message and the back-end will handle the register message. If the front-end receives the add message and the back-end is empty, we will print the service unavailable message. In another case, if the front-end has many back-ends, we need to select one of the back-end. Let's choose a random one and forward a message for it. When the front-end receives the back-end register message and this back-end doesn't exist, we need to add it to the back-ends and watch it. And of course, we need to handle the terminate message, which is received when one of the watching actors has terminated. We will remove it from the back-ends. And here is the initiating method that creates the actor system and front-end instance. Now let's take a look at the Our App object. We have created 1 instance of the front-end and 3 of the back-end. We send the add message to the front-end. Let's run our app. Yeah, Akka logs are very helpful to understand the state from every node for joining the state to upstate. And finally, our add message has arrived in one of the back-ends. Of course, you should take a look at Akka cluster documentation. That's it for this video. See you in the next video where we use routing. Welcome to the 3rd video in section 5. In the previous video, we introduced the Akka cluster and implemented a cluster system. In this video, we will take a look at cluster metrics. Then an introduction to routers, we'll introduce the load balancer, adding routers, and finally, add it to our cluster. Let's begin. In our example from the previous video, we have 1 front-end node and 3 back-end nodes. A front-end node has a list of back-ends, and for every operation it selects, a random back-end to handle it. Our front-end uses a random selection strategy for the group of back-ends connected to it, which is similar to the behavior of a router. As we know, Akka has multiple routing strategies implemented already, like the random or the round-robin strategy. It's also possible to implement a custom strategy. On top of that, there is the cluster metrics extension, which has an adaptive load balancing strategy that will select nodes based on the cluster metrics data. But what's cluster metrics and cluster metrics data? Cluster metrics report the system's health status back to Akka, and it can base its routing decisions on it. Every member node in the cluster collects data about system health, such as its used and max JVM heap memory, system load average for the past minute, CPU utilization. This data is used by adaptive load balancing to perform load balancing of messages to the cluster nodes. It uses the random selection of routines with probabilities derived from the remaining capacity of the corresponding node. Now, let's add a load balancer to our example. First, let's add the configuration for our router, which is similar to other routers, but with additional configurations. We will define something known as the metrics selector, where we will use a mix technique that works based on heap load and CPU data. We will define the cluster configuration. For this, enable a cluster, disable local routines, and specify the node role that will contain routes. That is our front end, which is similar to the previous front end, but doesn't have a back-end list. Let's create one here, a scheduled task which sends a message every 3 seconds. Now, the front end appears to be like the one seen in the previous videos. Let's create the back-end router now. The back-end is a simple actor, which handles one message. This back-end object is similar to the back-end seen in the previous videos. In the app object, we start 3 back-end nodes and a front-end node. Let's run our app now. Yeah, it's working. Beautiful. At the end of this video, we added a router to our cluster to route between back-end nodes. See you in the next video, where we will introduce and implement the cluster singleton. Welcome to the 4th video in Section 5, Creating a Singleton Actor in the Cluster. In the previous video, we introduced load balancing and learned how to add it in our cluster. In this video, we will take a look at the introduction to cluster singleton, its working and implementation. Let's get started then. We use a cluster singleton to ensure that we have exactly one actor of a certain type running somewhere in the cluster. You need a singleton actor in the following cases: a single point of responsibility for certain cluster-wide consistent decisions or coordination of actions across the cluster system, a single entry point to an external system, a single master, many workers, a centralized naming service or routing logic. But it has several drawbacks as well, such as the cluster singleton may quickly become a performance bottleneck. You cannot rely on the cluster singleton to be available non-stop. It takes a while to notice that the node on which the singleton is running has died. The singleton has to be migrated to another node. So you should be careful in using a singleton, and it should not usually be your first design choice. Now, let's discuss how it works. In this example, we'll assume the cluster is using auto-downing, such that unreachable nodes will be marked as down by the cluster leader. We have a cluster singleton manager that manages one instance of the singleton actor among all other cluster nodes or a group of nodes tagged with a specific role. This actor starts functioning on all cluster nodes or a group of nodes tagged with a role. On the oldest node, Cluster Singleton Manager creates the actual singleton actor as a child actor from supplied props. If the oldest node becomes unreachable, the cluster failure detector will notice. If auto-downing is enabled, or that node is by someone declared as down, then the cluster will. Then, a new oldest node will take over, and a new singleton actor is created. If you want to only talk to the singleton actor, you can use the cluster singleton proxy, which will route all messages to the current instance of the singleton. The proxy will keep track of the oldest node in the cluster and resolve the singleton's actor ref. And if the oldest node becomes unreachable, it will stash all messages until the new oldest node takes over and the new singleton actor is started. Now, let's take a look at our example. We have a master actor, which is a persistent actor. It receives work from the front end and stores until workers request it. Let's take a look at the implementation, that is, the master messages. We have 3 commands: register worker, request work, and work. And we have 3 events: add worker, add work, and update work. The implementation for the master will be such that when it receives register worker, it will persist the add worker event. When it receives request work and the work is empty, it will reply with no work. When it receives request work and requester on the workers, it will send work to it and persist the update works event. When it receives work, it will persist the add work event. Let's move to worker now. The worker is a simple actor that will handle one message, work. Now, let's complete our logic. We need to talk to the master, so let's create the cluster singleton proxy. The props of the proxy take the path of the singleton manager and cluster singleton proxy settings, which takes actor system and role. Let's assume that the name of the cluster singleton manager is a master and the actual singleton actor is active. Now, let's schedule 2 tasks. For every 30 seconds, we will send the register worker message, and for every 3 seconds, we will send the request work message. Let's concentrate on the front end now. This actor is set to send a message to the master every 3 seconds. So let's add a singleton proxy and schedule the task for every 3 seconds. Now, let's implement the app object. We will start 3 nodes, where every node has a cluster singleton manager and a worker instance, and one of them will contain the front end, that is, the actor. Here is the definition for the actor system and configuration. And we need that to start the shard journal. But remember, on production, this journal will be a single point of failure, and you should use a distributed journal. Now, let's add our singleton manager. We will use the cluster singleton manager, which takes props for the actual actor, termination message, and cluster singleton manager settings, which takes actor system, role, and name. We are finally done with the creation for our worker and the front end. Let's run our app. Yeah, our workers receive work from the front end via a singleton master. Good work! You can check the documentation from here. In the end, we have discussed how to implement cluster singleton. See you in the final video of section 5, where we'll work with cluster sharding. Welcome to the final video in section 5, cluster sharding. In the previous video, we introduced cluster singleton and saw how it can be implemented. In this video, we will take a look at what cluster sharding is, how it works, and how we can implement it. Let's get started then. If you need to distribute actors across several nodes in the cluster and want to be able to interact with them using their logical identifier without having to care about their physical location in the cluster, then cluster sharding should prove to be pretty useful. Cluster sharding is typically used when you have many stateful actors that together consume more resources like memory that can fit in one machine. This is even more powerful when used together with Akka Persistence, such that these actors can store their state and be recovered on demand. Now, let's discuss how cluster sharding works. A shard is a group of actors with an identifier, and these actors are called entries. Each node on a cluster involves running an actor called shard region. This actor is responsible for managing entries. A shard region starts with 2 application-specific functions to extract the entry identifier and the shared identifier from the incoming messages. In the first message in a specific shard, the shard region requests the location of the shard from a central coordinator. This is a sharding coordinator. A shard coordinator contains the location for every shard in the cluster and is a persistent cluster singleton. The reason it's a cluster singleton is because you want to make the shard allocation decisions atomically, which a cluster singleton can guarantee. Let's introduce 2 scenarios to understand the cluster sharding mechanism. Scenario 1. Incoming message M1 to shard region R1. M1 is mapped to shard S1. R1 doesn't know about S1, so it asks the coordinator C for the location of S1. C answers that the home of S1 is R1. R1 creates a child actor from the entry E1 and sends buffered messages for S1 to E1 child. All incoming messages for S1 which arrive at R1 can from now on be handled by R1 without C. In case the R1 node goes down, the process repeats, as the manager will have to reassign which region should now take care of this shard. Scenario 2. Incoming message sent from M2 to R1. M2 is mapped to S2. R1 doesn't know about S2, so it asks C for the location of S2. C answers that the home of S2 is R2. R1 sends buffered messages from S2 to R2. All the incoming messages for S2 which arrive at R1 can be handled by R1 without C. It forwards messages to R2. R2 receives a message for S2, asks C, and we are in the scenario like scenario 1. Now, let's start the implementation. Here is the configuration for our example like the previous examples, but we will add persistence configuration. This is a counter actor. It is a persistent actor that handles increment, decrement, and get messages. This is the definition of messages. Now, let's add the sharding logic. We need to add a wrapper for our messages. Let's call it a we_add_counter message, which contains an ID and a command. We now need to add an implementation for the ID extractor and shard resolver. The ID extractor is a partial function that takes any and returns a tuple of string and any, with the any being the message we want to deliver to the node. It is returning an identifier for entry and a message that will be forwarded to entry. A shard resolver is a partial function that takes any and returns a string. It takes a message and returns an identifier for the shard. Here is a front-end actor. It handles tick messages that contain increment, decrement, or get operations. First, we need a reference for the shard region to send messages to it. So we will get it from cluster sharding by the sharding name. Our sharding name is counter. Let's schedule 3 tasks. Every 3 seconds, we will send a tick message to itself with the increment operation. Every 6 seconds, we will send a tick message with the decrement operation, and every 10 seconds, we will send a tick message with the get operation. Now, let's take a look at our app object. We will start 3 nodes. Every node contains a shard region, and one of them contains the front-end instance. This is the important thing in a cluster, the Akka Persistence, which must be configured with a distributed journal. This is to start a distributed journal. Let's run the app. Here is our message. Every 3 seconds, the counter actor in the specific region receives an incremental message. You can download the example, run it, and watch the logs for yourself. We've learnt so much here, it really seems magical. And check the documentation here. At the end of section 5, we have introduced and played with Akka Cluster. We have implemented a simple cluster, load balancer, cluster singleton, and cluster sharding. See you in the next section, where we will learn how to test actors. Welcome to Section 6, Testing Actors. In the previous section, working with Akka Cluster, we were introduced to the Akka Cluster and touched upon topics such as remote actor, routing on the cluster, cluster sharding, and cluster singleton. In this section, we will shift our focus to testing different aspects of Akka. We will test our actors, parent-child relationships, and finite state machines. Finally, we will take a look at multi-mode tests. Let's start with the first video, how to test an actor. In this video, we will take a look at the different styles to test the actor, and we will start with coding. Akka comes with a dedicated module for supporting tests, the Akka Test Kit. Let's add the Akka Test Kit module and Scala test to our dependencies. Here is the counter actor, which handles the messages increment, decrement, and get count, and has a count variable. We want to implement our tests for this actor. Let's create a counterspec class that extends the testkit class, which gives us the basic tools we need to work with actors. This includes access to the Akka system, as well as helper methods for dealing with responses from actors under test. We will be using Scala test in this video. However, it's possible to test Akka using different testing frameworks. The test kit provided by Akka is test framework independent. In case of Scala test, we need to extend the flat spec like trait to get the general test syntax available, before and after all to be able to hook into the suite's lifecycle events, and we'll use the must matches to actually write our assertions using the X must do something style. First, let's shut down the Akka system after all the tests finish. For this, override the after all method. We will use the shutdown Akka system method from testkit as our Akka system was created by the test kit called system. Now, let's add our test unit. First, let's define our sender actor that will send messages for our counter actor. We will use test probs, which allows us to send messages and expect response messages. Next, let's define running an instance from our actor, send an increment message, and then get the count message. Now, our sender should receive the response of the get count message. Test probs provide some methods that help us to expect the messages. Let's use expect message type, which expects a message of a specific type. Our response should be int. If the sender receives a message with another type, this expectation will fail. Finally, let's assert on the value of the state. The state must be equal to 1. Let's run. Great, it passes. Let's implement a test unit for increment messages only. We do not want to set up a test probe each time in a test. We can instead use the implicit sender trait, which makes the test kit able to receive messages directly. The test kit contains the test actor, which contains expectation methods such as test prob. When we mix with implicit sender, this test actor uses as a sender for any message in tests. So let's define a running instance of a counter and send an increment message for it. When the counter actor receives an increment message, it just changes the count and doesn't send a response to the sender. So, let's expect that we didn't receive messages during that 1 second slot. Here we are using the implicit sender. Let's run. Great, it passed as well. Now, let's add a test unit for the decrement message like the previous one, but we will send a decrement message and also expect no message. Let's run. Great. Now, let's add a test for get count, but we will use an implicit sender and send the get count message only to make sure our actor starts with 0 on the count variable. So, let's add an instance of the counter, send the get count message, and expect we will receive the message containing 0. Let's run. Excellent! Now let's add another test, where we will send the increment, decrement, and get count messages. Let's create an instance of the counter, then send 2 increment messages, send a decrement message, and also send another increment message. Now, the counter actor should contain a count that equals 2. So, let's send the get count message and expect to receive a message that contains 2. Let's run. Excellent! All tests passed. At the end of this video, we implement a different unit test for each counter actor. We use the recommended style from Akka. You can check the test documentation from here, and you'll find another style for testing called synchronous testing, which uses test actor ref, but it's potentially exposed for race conditions and should not be used. See you in the next video, where we will test parent-child relationships. Welcome to the second video in Section 6, Testing the Parent-Child Relationships. In the previous video, we tested the counter actor using different styles. In this video, we will take a look at how to test the relationship between a parent and child. Let's get started. We have 2 actors, parent and its child. Here is a child actor. Its purpose is very simple. When it receives a ping message, it sends a Pong message to its parent. Here is a parent actor. It contains a child and a ponged variable. It handles two messages, ping it and pong. When it receives a ping it sends a ping message to the child actor. When it receives a pong message, it changes the ponged variable to true. We now need to test these actors. Let's start thinking about test scenarios for a child actor. It's a simple actor. We need to test when it receives a ping message. It will send pong message to its parent. But in such an implementation, we can't implement our test scenarios because we need to make sure a parent actor receives the pong when we send a ping message to the child actor. We need a reference to a parent actor to complete our test, so we will make some changes to our implementation. For this, we will change the child's constructor to take a reference for his parent. And we will avoid using context.parent and will instead use a reference that is defined on a constructor. Now, let's write our test case. First, we will define a parent as a test probe. Then, let's define an instance of the child. Now, let's send a ping message for the child, and as our expectation, the parent should receive a pong message. Let's run tests and check whether our expectation is right or not. Great! Now, let's move to parent tests. Let's think about a test scenario. We need to make sure when a parent receives ping it message, it will send ping message to its child. But we face the same problem here. We don't have a reference for a child actor. So, let's change a parent's constructor to accept a child maker. It's a function that takes actor_ref factory and returns actor_ref. Let's just change the child creation. Now, let's write our test. First, we will define a test probe that will represent the child's probe. Then we'll define the child maker. We will define the functions such that whatever it receives, it will send an actor reference for the child probe. Then, we'll define an instance of the parent. Now, we will send a ping it message to the parent. As expected, our child should receive a ping message. Let's run tests. Excellent! As shown, we might need to change our implementation to be testable. At the end of this video, we have tested the parent and child actors using the dependency injection approach. See you in the next video to test the FSM actor. Welcome to the third video on Section 6, Testing Finite State Machines. In the previous video, we tested our parent and child actors. In this video, we will take a look at revisiting the user storage FSM example from Section 3 and how to test an FSM actor. Testing actors should always be done via messaging. However, with finite state machines, it is sometimes useful to drop down to using the FSM test actor ref. It is also unsafe, in the same way as text to act ref is. However, let's see what additional tools it provides. Remember that you can always test an FSM actor like any other actor using the recommended way, plain messaging and test probes, as explained in video 5.2. Let's get started. Here is our example from Section 3, User Storage FSM. Let's revisit our FSM actor logic. User storage has started on the disconnected state. If it receives a connect message, it will be in the connected state. And if it receives any other messages, it will stay in the disconnected state. In the connected state, if it receives a disconnected message, it will switch the disconnected state. And if it receives any other messages, it will stay in the connected state. So, let's test this logic. Akka comes with a special type of test actor ref named test FSM ref. This special type offers all features of a normal test actor ref, and in addition, allows access to the internal state. So we will use this type in our tests. Let's start with the first test case. We want to make sure our FSM actor starts in the disconnected state. So we will need to define the test instance from the user storage FSM, and then assert on state and data. Test FSM ref contains two important methods, state name and state data. In our case, state name must be equal to disconnected, and state data must be equal to empty data. Let's run our test. Excellent! It works as expected. Now, let's move on to the next test. We want to make sure when our actor receives a connect message in the disconnected state, it will switch to the connected state. So, let's add a test instance for our actor. Then, we will send the connect message. Now, let's check the actor state and data. Let's run tests. Great! It's all green. Now, let's move on to the next scenario. We want to make sure when our actor receives any other messages in the disconnected state, it will stay in the disconnected state. So let's add a test instance for our actor. Then we will send a create message. Now, let's check the actor state and data. Let's run tests. Excellent! Works again. Great going. We're on the right track. Here is another test case to make sure when it receives a disconnect message on the connected state, it will switch to a disconnected state. And here is a last test to make sure when it receives DB operation messages on the connected state, it will stay in the connected state. Let's run all tests. Excellent! All tests passed. I think the idea is clear now as to how to test FSM behavior. Of course, you need to add more tests to make sure that your business logic is correct, but in this video, we were able to check how to ensure our FSM logic is correct. See you in the next video to test multinodes. Welcome to the last video on Section 6, Multinode Testing. In the previous video, we tested the FSM actor. In this video, we will take a look at multinode testing, which among other things can be used to test Akka cluster apps in an almost real setting, with real networking involved between the JVMs. Here, we will get a quick introduction to multinode testing kit, and we'll discuss the main parts on it. And finally, we will implement multi-node test examples. We'll be running the tests on the same physical machine, so this style of testing is most often referred to as multi-JVM testing. On the same machine, many JVMs, as opposed to the multi-node, which refers to many JVMs on many nodes in the network. The interesting thing is that the API is exactly the same, and we can decide later on where to run these tests. Let's head straight into it. Before we start, let's answer the important question. What's multi-node testing? Multi-node testing means we want to run coordinated tests on multiple actor systems in different JVMs, potentially even on different hosts in a network. This means you want to actually execute a test on different JVMs at the same time. First, let's discuss the main parts in the multi-node testing kit. We have three main parts. The test conductor is the basic part of the multi-node testing kit. It is used to coordinate the nodes participating in the test. The multi-node spec is a convenience wrapper for starting the test conductor and letting all nodes connect to it. The SBT multi-JVM plugin is an SBT plugin that starts tests in multiple JVMs, possibly on multiple machines. Let's start coding. First, we need to prepare our project for multi-node testing. We will add SBT multi-JVM plugin in the plugins.sbt file. Then, here's our build.sbt file. It looks different now because we defined some additional settings, such as compile multi-JVM tests by the test default compilation, execute multi-JVM tests by the default test target, and merge the multi-JVM test results with normal test results. Now, let's revisit our worker actor that is a remote actor from the first video in Section 4. It was handled using work messages. We will make it reply to the sender with done message as well. Now, let's start writing our tests. Our multi-node tests are located in the src/multi-jvm directory. We will create our package under this directory. Then we will implement multi-node tests in 3 steps. Define multi-node configuration, then define the basic test trait, and finally, write our tests. First, we need to define our multi-node configuration. In this configuration, we define our nodes and the role for every node. Let's say we have 2 nodes. One of them is a node 1 and another is a node 2. Second, we will define the basic trait for our tests. Let's name it Basic Multi-Node Spec, and this trait will extend multi-node spec callbacks, flat spec like, must matches, and before and after all. We will override the before all function to call the multi-node spec before all function, and override the after all function to call the multi-node spec after all function. Finally, let's write our tests. Let's define the multi-node sample class that extends multi-node spec, basic multi-node spec, and implicit sender. The first thing we need to implement is the initial participants function, which defines the number of members in the Akka cluster for starting the test. So let's say it is equal to the role's size. Now, let's write the first test case. In this test case, we will need to make sure our test waits until all the nodes start. So we will use the enter barrier function, which takes the barrier name. This means the test conductor will wait until all the nodes start up. Let's write the second test case. In this test case, we need to start the worker instance on node 2, and on node 1, we will find a worker reference and send work message for it. And of course, we want to make sure node 1 will find a worker instance after it's created on node 2. For this, we will use barriers that come within the multi-node test kit. Let's imagine a barrier is a point. The node may be doing some work before this point or after this point, but the important thing is no one crosses this point until everyone has arrived at it. And this is the responsibility of test conductor. Let's start. We will use the run-on function, which takes a node name and block of code to run it on the node. In node 2, we will start an instance of worker, and this node will set enter barrier to deployed. On node 1, after all the nodes have reached the deployed barrier, we will define a worker using the actor selection, and then we will send a work message for it. And finally, we expect to receive a done message. And after our code runs on every node, we will reach the finish barrier. Now, let's define our test classes that will run on the node on a different JVM. So we will add 2 classes. Every test class must end with the multi-JVM followed by the node name. And these classes will extend the multi-node sample class. Let's run our tests. Great! You can check the full documentation from here. At the end of this section, we have learned how to test the actor in different styles. Then we tested parent-child actors, and finally, multi-node testing. See you in the next section, where we will work with a new feature called Akka Stream. Join me there. Welcome to Section 7, Akka Streams. In the previous section, we introduced you on how to test actors. In this section, we will introduce the new module in Akka, that is, Akka Streams. At the moment of recording, Streams are in version 1.0 experimental, and slight API changes may still happen. However, it's stable enough to be used already, so let's take a look. Here we will take a quick look at Intro to Akka Stream and its terminologies. Then, we will implement our Stream application, Reactive Tweets, and test the Reactive Tweets application. We will then work with graphs and with Stream I/O. Let's start our trip in the Stream world. In the first video, we will take a look at the problems of fast data and streaming processing world and why we should be using Akka Streams. Next, we will introduce the basic terminology in Akka Streams and implement our first Stream app. Let's start then. Big data has been around for quite a while, and it's usually batch processing. In the current world, though, we're starting to talk about fast data, which means we want to process the data right away when it hits our servers, for example. Akka streams are a library which allows implementing either style of application and guarantees that it'll execute on bounded buffer sizes, will not cause out-of-memory errors. The two main problems streaming data solutions need to tackle are blocking and back pressure to survive high-load scenarios. Blocking can happen in a pull-based system. This means a consumer pulls data from the producer. Blocking takes place when there is no data to pull. This is safe for the consumer. It will not run out of memory. However, it is also very slow to build systems based purely on pulling data. The other problem is back pressuring too fast. Producers of data when working with pushing data. In pull systems, it's not as visibly needed. However, they are slow, and we want our systems to be fast. The need for back pressure arises when the producer wants to create more data than the consumer can handle, which can cause the consumer to crash. Let's take a real-life example to understand these problems. Let's imagine we have a source of water and a sink, which we want to fill, and we have pipes between them. If we decided to put a pump at the end of the pipes to pull the water, the pump will still work, even if there is no water on the source. And if we move the pump to start off the pipes to push the water, the pump will still work, even if the sink is filled and the water just overflows. To fix our problems, we need to put a pump on the source and cap on the sink. This means the pump will work when a source contains water. And when the sink fills, the cap will create back pressure and trigger the pump to stop pumping. This is exactly what Akka streams do when it comes to solve the main problems on streaming data processing. Akka streams describe the solution as asynchronous dynamic push-pull back pressure. Now, let's discuss the main parts of Akka streams. The main elements of Akka streams are source and sink. The source is where data begins to flow from. It has the output port and no input port. The source in our example may be a river. In applications, it may be a query from the database or HTTP request bytes. The sink is the end of the stream. It has the input port and no output port. In our example, we were directing the flowing water that we have collected in a sink. In real-world applications, it may be the stored data in the database or data written on a file, so we'd have a file sink. As streams can have multiple processing stages between a source and a sink, we also need to name this concept. In Akka, it's called a flow, and one can flow the data via a flow, from source via flow, and finally to a sink. If you want to make things more interesting on the stream, you need to add a flow between the source and sink. A flow can be used to apply transformations to the data coming out of a source before putting it into a sink. When connecting the source to the sink, we get a runnable flow. A runnable flow is something we can start. In other words, it's a flow with a sink and a source attached, a complete stream pipeline. This is the most basic complete form you can make in Akka streams. This means you must connect your source with a sink to have a complete system, and your data can flow through it. Now, let's implement all this into a simple app. Akka Streams provides this nice type-safe DSL to build streams from. The actual execution of it is actually handled by actors underneath. Here's how we can build and run a simple stream. We will talk about them in the next video. First, let's define our source. Let's say we will generate iterators from 1 to 100. Next, let's define a flow. Let's say we want to multiply it by 2. Then, let's create our sink. In our sink, we will print the elements. Now let's run our app. Voila! Our stream app is working. This is a simple application, but we have used all the basic elements on it. See you in the next video, where we'll implement another stream application, reactive tweets. Welcome to the second video in Section 7 on implementing reactive tweets. In the previous video, we introduced Akka Streams and implemented a simple app just to understand the basic concepts. But this video has a different story to tell. In this video, we will take a look at the logic of our application and prepare our project for Akka Streams, and finally perform its implementation. Let's jump right into it. Let's say we don't want to spend a lot of time on Twitter, but we are interested only in tweets about Akka. So let's retrieve all tweets from the Twitter API, and then we will filter them to show only tweets about Akka. Let's begin coding. First, let's add an Akka stream module on our dependencies. We will use Twitter, the Twitter Java API. Now, let's take a look at the Twitter client object. We have two methods. The first one to create a Twitter client instance, and the other one to retrieve 100 tweets based on the query term. Now, let's define our types. We have the author case class that contains the author's name, and we have the hashtag case class that contains the hashtag's name, and this name must start with hash. Finally, we have a case class to represent a tweet that contains the author and the body of the tweet. We will add a function to it to extract hashtags from a tweet. Now, let's play with Akka streams. First, let's define our source that will be an iterator of tweets. Now that we have an iterator of tweets in Twitter form, we need to transform them to our representation. So, we need to define a flow that transforms the Twitter structure to our structure. We defined our source and flow. Let's define the endpoint of our stream. In the sink, we just need to print tweets. Now, let's connect our source with flow and sink. The via function takes a flow and returns a new source. And the runWith function connects a source to a sink and returns a materialized value of the sink that means a result of the sink that is a unit on our example, because we are just printing tweets. Materialized values are an advanced concept of Akka streams. Feel free to dive into the documentation for it. And then, once the stream has completed, which could be never in the case of infinite streams actually, we need to shut down our Akka system. Let's run our app. Great! Now, let's return to our code. Here, we have defined an Akka materializer, but we don't know what this Akka is and why we need to define it. To understand this, we'll need to take a step back and think about what materialization actually means in Akka streams. In the software teams, a project owner has to plan for his project, but he doesn't need to manage team resources or make a schedule for his plan. He is just interested in getting results, not the actual progress or how it will execute. So he gives his plan to the team leader. And the team leader is responsible for executing the plan by allocating all resources from his team and making a good schedule. Once again, let's take a look at our code. Here we are defining our stream. We define a source of the stream, then we define some transformation via a flow, and then we define sync, which is the endpoint of the stream. These three steps are like a plan. We want to take tweets, convert them to our structure, and then print them. We want a team leader to take our plan and execute it. So Akka streams separate the plan from the materialization for us. First we lay out the plan, and then we ask the leader to materialize it. This leader is a stream materializer, and the default provided implementation by Akka is based on actors, of course, and thus the name Akka materializer. It materializes the stream into a set of worker actors. This actor is responsible for allocating all the necessary resources it needs in order to run your plan. But we define it as an implicit variable. Who needs it in our code? Your assumption is right. We only need it at that point in time where we materialize, also known as the run stream. In other words, it is a runWith function that uses it. At the end of this video, we have implemented a reactive tweet example and discussed what a materializer actor is. See you in the next video, where we'll introduce how to implement tests for streams. Welcome to the third video in Section 7, Testing Streams. In the previous video, we were implementing the reactive tweets application, and I hope you checked the complete example code. In this video, we will take a look at different ways to test source, sync, and flow. We will test source, sync, and flow using the following methods: simple sources, syncs, and flows, using actors, using Akka Stream Test Kit. Let's play with the first method. We will start with sync. Let's define a sync that we want to test. Let's say it's a very simple fold that will sum all elements of a stream. We know the stream we'll use is finite, so this is safe. Now, we define a simple source. Let's say it is an iterator from 1 to 4. If we run the source with our sync, the result should be 10. So let's connect source to sync. Once we run the stream, it materializes a value of future long, which is the result of the fold operation once the stream finishes. Our result is a future, so let's use the await function. This result then must be 10. Let's run our test. Great. Let's move to source. Let's say we have a source that produces iterator numbers from 1 to 10. Such a source can be tested by asserting that first arbitrary number of elements. We will group this source by 2. This means the group will chunk up this source for 5 groups. Then, let's connect this source to sync, which returns the head of it. So our result must be a sequence that contains 1 and 2. Let's run. Excellent. Now let's move our attention to flow. Let's say we have a flow that takes a number less than 5. Let's try this flow with a source that contains an iterator from 1 to 10 and a sync returning the fold element to list. Our result must be a sequence from 1 to 4. Let's run. Great. Now, let's play with the second approach. Akka Stream offers integration with actors out of the box. This support can be used for writing stream tests that use familiar test probe from the Akka Test Kit API. Let's test the source. We have a source that contains a number from 1 to 4, and we will chunk it up to 2. Let's define our test probe, which will receive the results. Now, let's connect our source to sync that returns the head and then pipe it to our test actor. Now, let's expect that our test actor receives a sequence of 2 sequences. Let's run the test. Great! Let's test a sync now. First, let's define a source that generates a tick every 200 milliseconds. Then, let's create a test probe and a sync that sends the elements of the stream to the given actor. The actor_ref function takes an actor_ref for our actor and the message that will send when the stream is completed successfully. Now, let's define our runnable. Now we should expect a tick message. Then for 100 milliseconds, we expect we don't receive anything, and after 200 milliseconds, we will receive another tick message. Let's cancel our runnable. So we should receive a complete message. Let's run. Excellent. We can use actor_ref from source to get full control over elements to be sent. So let's use it. Let's define a sync that converts int to string and will concatenate these strings. Then, let's define our source using the actor_ref function that takes the size of the buffer in element count and the strategy that is used when incoming elements cannot fit inside the buffer. Then, let's create our runnable and run it. This will return our future result and actor_ref for a source. Now, let's send some messages to this ref. And then let's expect our result. Let's run. Great. Now it's time for Akka Stream Test Kit. The Akka Stream Test Kit provides test source and test sync. We will use test sync when we want to test the source, and test source when we want to test the sync. Let's start with testing this source. Here, we have a source containing 4 elements, and perform a filter and map operation on it. Now, let's run this source with test sync. The probe function from test sync will materialize a sync to a test subscriber. And this has a lot of useful methods that will help us on the test, like a request function that we use to request a number of elements until we request some element. The stream is back-pressured and won't actually generate the values because it needs demand, us requesting elements, to make it run. Our stream should contain 2 elements, so let's request 2. And we will use expect next that takes elements, and then we expect the stream to complete. Let's run. Great. Now let's use test source. Let's define our sink, that is simpler. Then let's connect this sink with the test source. We should just expect a cancellation. Let's run. Excellent. See you in the next video, where we will introduce a new concept on Akka streams, graphs, and see how we can work with it. Welcome to the fourth video in section 7, working with graphs. In the previous video, we implemented test cases for streams. In this video, we will take a look at how to model advanced processing structures using flow graphs and how we can implement them. Let's start. In the previous videos, we worked with flows that have one input channel and one output channel, and we explained our streams as a linear sequence of steps, also known as flows. But not everything can be expressed as a linear sequence. So, to tackle this, Akka Streams comes with a graph flow. Graphs are needed whenever you want to perform multiple input or multiple output operations. Akka Streams currently provides some default junction implementations, which can be fan-in, many inputs, one output, or fan-out, one input, many outputs. The fan-in junctions are: merge takes n number of inputs and returns one output and picks randomly from inputs, pushing them one by one to its output. Merge preferred is like a merge, but if elements are available on the preferred port, it picks from it, otherwise randomly from others. Zip with takes a function of n inputs that, given a value for each input, emits one output element. Zip is a special case of zip with, which takes two input streams and zips them into a tuple of the stream. Concat concatenates two streams, first consume one, then the second one. Fleximerge enables writing custom fan-in elements using a simple DSL. And fan-out junctions are broadcast, which given an input element emits to each output. Balance, which given an input element emits to one of its output ports. Unzip with, which takes a function of one input that gives a value for each input, emits n output elements, where n must be less than or equal to 20. Unzip, which splits a stream of A, B tuples into two streams, one of type A and one of type B. Flexiroute, which enables writing custom fan-out elements using a simple DSL. Now, let's see the graph we need to implement. Here is our stream plan. We have a source that connects to a flow F1. Then F1 will be an input to broadcast the junction, which generates two flows, F2 and F4, which then merges to a flow F3 that will be an input for our sink. Let's implement this graph. Now let's define our source. Let's say we have an iterator from 1 to 10. Our sink will print each element. From our graph, we have 4 flows. Let's say F1 and F3 will add 10 for every element. F2 will multiply by 5, and F4 will add nothing. For now, we don't define new things. Now, let's define a flow graph. We will use a closed function from the flow graph object, which takes a builder block and returns a runnable graph. Now, let's define a builder block, which is a function that takes a builder of unit and returns a unit. In the body of this function, we will describe our graph steps. Let's revisit our graph. We will use broadcast and merge junctions. So let's define them now. We will use the add function from the builder instance to add broadcast, which has 2 outputs. And we will add the merge junction, which has 2 inputs. Now we need to draw our graph. So we will use graph DSL. The DSL is designed to look similar to how you draw a graph on a whiteboard. You use the arrows to connect various components of it. Akka Streams has Graph DSL that enables to translate graphs from the whiteboard to a simple code. We use it via an operator, so let's import it implicitly from the GraphFlow object. So our graph will be in via F1 via broadcast, via F2, and F4 via merge, via F3 via out. We describe our runnable graph, but we haven't run it yet. So let's run it. Excellent! The results are as expected. At the end of this video, we implemented a simple graph flow and used just 2 junctions. I want you to pull our example and try other junctions as well for practice. See you in the next video, where we'll introduce Stream I/O and of course implement it using examples. Welcome to the last video in Section 7, Working with Stream I/O. In the previous video, we are introducing graph flow and implemented it, and I hope you are playing with graph flow junctions. In this video, we will take a look at Akka Stream I/O and its implementation. Let's start. Akka Streams provide a way of handling file or TCP I/O with streams. This means Akka Streams provide simple sources and sinks that can work with byte string instances to perform I/O operations on files. Let's implement our example. First, let's create our source. Let's create a generator of random numbers and filter to get only prime numbers. Then, let's define synchronous file sync that takes a file. The name synchronous file sync may seem a bit weird, since Akka is all about async. However, it's not that scary as it may sound. It simply refers to the underlying I/O APIs that it is using, which are synchronous. The blocking code is carefully separated from the reactive parts of the application for us, so we don't need to worry about the blocking when using this sync. Once Akka Streams will require JDK8, an asynchronous I/O sync will be provided by the team. Now, let's define file sync, which is a flow that transforms every number to byte string and then will connect this flow to our sync by using toMap function. This will generate a new sync. Next, let's create console sync, which prints numbers on the console. Now we have 2 outputs for which we need a graph flow. Let's create a graph flow with file sync and console sync. And in the body of the builder function, we will define broadcast with 2 outputs. Let's now define our graph. We connect the source to broadcast and connect broadcast to file and console. And of course, we shouldn't forget to run our runnable. Now let's run our app. Great, our console sync is working. Let's check the file. Excellent. Now let's implement the source from a file. Here is a log file. We will read it and print these lines on the console. First, let's define our file and a source. We will use a synchronous file function from a source object to create our source. One can get access to the I/O syncs using the import akka.stream.io implicits ... to get sync.synchronous source, or one can type synchronous file sync directly. The syncs factory method takes a file object. Then we need to pass chunks of bytes into lines. Now let's create our flow. We will use framing object to create a flow that handles decoding a stream of unstructured byte chunks into a stream of frames. We use a delimiter function that takes delimiter, maximum frame length, and allowed truncation. And then we will map them to UTF-8. Now let's define our sync that will print on the console. Let's connect the source with the flow and run them with sync. Let's run our app. Great, this is the file content. At the end of Section 7, we have learnt how to work with Akka Stream. That was just an intro to Akka Streams, and it's currently an experimental module. However, it has been already tested and proven to be a valuable part of Akka and is here to stay. Its experimental status means that some parts of the API may change slightly in an upcoming release, but nothing too drastic is expected to change. See you on the next section, Akka HTTP. Welcome to Section 8, Working with Akka HTTP. In the previous section, we were working with Akka Streams. We have looked into the main parts on Akka Streams, sources, flows, and sinks. And we were working with graphs and Stream.io, and finally, we tested them. In this section, we will introduce another module of Akka, Akka HTTP. We'll do a quick introduction to the Akka HTTP module and work with the client-side and server-side APIs. We will then implement a RESTful API server and introduce testing. Let's start with the first intro video. First, we'll look at how the HTTP module fits into the Akka ecosystem, and then we'll see which modules it itself is composed of. Let's start. Akka is a toolkit for building highly concurrent and distributed applications. When you think about distribution, you think about how to integrate the stuff that we've just distributed. If you want to distribute your application across threads, Akka gives you actors. And when you want to distribute your application across machines, Akka gives you Akka Cluster and Akka Remoting. When your application wants to interact with external services, Akka gives you Akka HTTP, since HTTP is the de facto standard of many web-based applications. And the whole world talks using this protocol. It makes sense when you want to talk to the external world, you use HTTP module. Akka HTTP isn't a web framework. It's a toolkit for providing and consuming HTTP-based services. This means the main goal of Akka HTTP is to integrate your application with the external world. And if you think about implementing the web application that has a lot of views, it needs to prepare assets such as images that compress JavaScript and CSS, and so on. Thus, it is better to choose the web framework Play rather than Akka HTTP. The Akka HTTP module is implemented on top of Akka Streams, which are implemented on top of Akka Actors. Each layer provides additional capabilities and/or limitations to what you can do with them. It has a full server and client-side HTTP 1.1 stack. In other words, if you want to talk with the external service, you will need to use a client-side API. And if you want to provide a service to the world, you will need to use a server-side API. Akka HTTP is structured into several modules. Akka HTTP Core, which contains a complete low-level full-server and client-side implementation of HTTP, such as a connection and TLS management. Akka HTTP, which contains higher-level functionality, such as marshalling, compression, decompression, as well as a powerful routing DSL for defining HTTP-based APIs on the server side. Akka HTTP Test Kit, which contains a set of utilities for verifying server-side service implementations. Next, we have Akka HTTP Spray JSON, which contains a predefined glue code for serializing and deserializing custom types from and to JSON with Spray JSON. It is possible to use Akka HTTP with other JSON serializers, and there exist community projects providing these integrations if you prefer to use something other than Spray's JSON library, which is very fast but requires a bit of coding to set up. Lastly, we have Akka HTTP XML, which contains a predefined glue code for serializing and deserializing custom types from and to XML with Scala XML. At the end of the first video on Akka HTTP, we just introduced Akka HTTP module and its structure. In the next video, we will work with client and server-side APIs. See you there! Welcome to the second video in Section 8, Working with Client-Side API. In the previous video, we were introduced to Akka HTTP module, and we discussed its structure. In this video, we will take a look at different levels on the client-side API: connection level, host level, request level. All functionality of client-side is implemented in the Akka HTTP Core module. Akka HTTP client-side API provides 3 different API levels. Depending on your application's needs, you can choose from these levels. Very simple apps may stay on the request level API, and more advanced and performant ones may want to choose the other APIs. The connection level API is the lowest level client-side API. It gives you full control over when HTTP connections should be opened and closed, and how requests are to be sent across which connection. The host level API is built on the top of the connection level API, but it autonomously manages a configurable pool of connections to one particular target endpoint. This means Akka HTTP will manage a connection pool for you. The request level API is built on the top of the host level API to provide you a simple and easy-to-use way of retrieving HTTP responses from remote servers. Akka HTTP performs all the connection management. It is the most convenient way of using Akka HTTP's client-side functionality. Let's implement our examples with 3 levels of client-side API. We want to get our IP information using the Teles API. First, let's define our IP info class. It will be a case class that contains IP, country, and time zone. The response will be a JSON object, so we need a format, which will convert JSON objects to our class. So, let's define our JSON protocol object that will extend default JSON protocol from spray.json package. This object will contain an implicit format for our class. This format means we are able to read, write it to from JSON. Now, let's play with the connection level. Akka HTTP is implemented on top of Akka streams. So, let's think about request and response like a stream. HTTP will provide us with a flow that will consume HTTP requests and provide HTTP responses, all using the same connection. This has the potential of being faster than reconnecting each time you want to send a request to a service. So, we need to define a source of requests and a sink for the responses. First, let's define a connection flow such that its input will be HTTP request, its output will be HTTP response, and its materialized value will be outgoing connection type, which represents a prospective outgoing HTTP connection. We will use the outgoing connection method to create our flow. Then, let's define our stream. We will use the single function from the source object that takes a URI to define our source. Next, let's connect it with our connection flow and run it with sync. That is a feature of HTTP response. Let's map on it and print our response. If the status of response is OK, let's unmarshal the response entity and convert it to our IP info class, and then let's print it. If the status of the response is otherwise, we will convert the response to string and print it. Let's run. Great! Here is the information of my IP. Now, let's play with the host level. In this level, we will let Akka HTTP manage our connection pool for a specific endpoint. So, as the first step, we will create a pool of connection. We will use the cached host connection pool function that will return our flow, which is also called a pool client flow. This flow consumes tuples of type HTTP request, T, and produces tuples of type try, HTTP response, T. The API includes an object of type T with the request and the response. Think about this object as an identifier to identify this response for this request, because our pool will have more than one connection and generates responses in an order that doesn't directly match the consumed requests. So, on our example, we'll just use an integer value. Now let's create our stream. We will use a single function from the source object again, but this time we'll take a tuple of HTTP request instance, and our identifier, let's say, will be 4. Then let's connect our source to pool client flow and run it with sync. And here is the handling of the response. Let's run the test. Great! Now let's move to the request level, which is a very common way to use client-side API. It's very simple. We will use a single request function from the HTTP class that takes the HTTP request instance. Here, we now have the same code for handling a response. This API is the simplest, yet most limiting of APIs. I'd recommend starting out with this API in your applications, and if you see the need to move to another API for performance reasons, you know how to use the other APIs already. Let's run. Excellent! We can now successfully work with client-side APIs. See you in the next video, where we will work with server-side API. Welcome to the third video in Section 8. Working with server-side API. In the previous video, we were working with the client-side API and we implemented our example using connection level, host level, and request level. In this video, we will take a look at low level and high level of server-side APIs. Let's get started. The server-side components of Akka HTTP are split into two layers. The basic low-level server implementation in the Akka HTTP core module, the higher-level functionality in the Akka HTTP module. The low-level server is scoped with a clear focus on the basic and necessary functionality of an HTTP server, such as a connection management, parsing and rendering of messages and headers, timeout management for requests and connections, response ordering, as well as things such as managing TLS for secure connections, and so on. But all high-level features such as routing, simplified file serving, or compression are implemented in high-level APIs. In high-level APIs, Akka HTTP provides a very flexible routing DSL for smoothly defining RESTful web services. Depending on your needs, you can either use the low-level API directly or rely on the high-level routing DSL, which can make the definition of more complex service logic much easier. Let's implement the Hello World server. We will start with low-level implementation. Akka HTTP is implemented on top of Akka Streams. So, when we need to implement anything on low-level APIs, server or client, we think about streams. What is our source? What's our sink? And what's our flow? A socket binding is represented as a stream of incoming connections. The application pulls connections from this stream source and, for each of them, provides a flow to translate requests into responses. A socket bound on the server side as a source, incoming connection, and each connection as a source, HTTP request, with a sink, HTTP response. So, the first thing we need to do in the low-level API is defining the server source. We will use a bind function that takes host and port and will return source, incoming connection. Now, let's create the HTTP server stream and run it. Let's connect our source to a sink for each connection on our sink. We will print a message. Incoming connection instance contains the remote address and some methods to provide a flow that handles requests coming in over this connection. Requests are handled by calling the handleWith method that takes a flow, the handleWith sink handler method that takes a function of HTTP request and HTTP response, or the handleWith async handler method that takes a function of HTTP request and future of HTTP response. We will use handleWith sync handler, which means that the flow we've given to HTTP synchronously converts a request to a response. Of course, internally, it may do an asynchronous operations. Now, let's define the request handler. In case HTTP request has a method, get, and URI for root, we will generate HTTP response containing the hello message. Otherwise, we will generate HTTP response with 404 status. And these to unbind our server and shut down the actor system when we press enter on shell. Now, let's run our simple server. Our server is running. Let's check from the browser. Yeah, it's working. Let's try any URL. Yeah, it's a 404 message. Excellent. As you can see, Akka HTTP is a full web server. It prints error messages and hints in case the user ends up on the wrong page, and so on. Now, let's use the high-level API. Instead of defining the flow or function that handle requests, high-level APIs provide a flexible, domain-specific language for expressing your service behavior as a structure of comparsable elements called directives. So, we will use the routing DSL to define our route. This is the structure form of the route block. So, let's define our route. Our path will be the route, and our method is a get, and on completion we will return a hello message. Now, let's start our server. We will use a bind and handle method that starts a new HTTP server, and we'll use the given handle to process incoming connections. Now, let's run the server. Our server is running. Let's check from the browser. Yeah, it's working. So, to wrap things up, we were introduced how to implement a simple server in low-level APIs and high-level APIs. See you in the next video, where we will implement the REST API. Welcome to the fourth video in Section 8. Let's implement a RESTful API service. In the previous video, we are introduced how to work with server-side APIs, and we implemented a simple server by low-level and high-level APIs. In this video, we will implement REST APIs for tweets. We will create, get, delete, and retrieve all tweets. Let's get started. First, let's prepare our project. We will need the Akka Stream module, the Akka HTTP core module, the Akka HTTP module, the Akka Spray JSON module, and the reactive Mongo module. Now, let's define our model. We have a tweet object that we will represent by a case class that contains the author and body. Let's define the JSON format for the tweet class. We will extend default JSON protocol from Spray JSON. And here is tweet entity that represents the tweet object on the database. It contains the ID, which is bson object ID, and by default we will generate the ID that contains the author and body. This is the tweet entity object that contains read and write bson, and the method to convert a message from a tweet to a tweet entity. Here, we also have a JSON format for the tweet entity class. Now, let's move to implement MongoDB object, which is responsible for connecting it to the DB. We will load the configuration to our database configuration. Let's read the database name from the configuration and servers list from the configuration object. Now, let's define an instance from Mongo driver and create a new connection and database instance. Now, it's time to define a tweet manager that is responsible for database operations. First, let's define our collection. We will define bson collection and our collection name as tweets. We should implement these functions: save, find by ID, delete by ID, and find. Let's start with the save function. We will use the insert function from the collection object, which will return future. We will map the result to return the created instance with an ID. For find by ID, we will use the find function to select an object by ID. For the delete by ID function, we will use the remove function and map the result for our deleted object. And finally, for the find function, we will use find with the empty query to get all the documents in the tweets collection. Then, we will make a cursor for this query. Now, let's define our route. All routes will start with tweets, so let's use path prefix with tweets. We need to define 4 URLs to create, get, and delete the tweet and retrieve all tweets. For creating, we will define post and request entity will be a tweet. We will call the save method from the tweet manager and map it to our response that will be a tuple of status and body. For reading the tweet, we will define get and our path will contain a segment. We will use find by ID and map the result to our response. For deleting the tweet, we will define delete and our path will contain a segment. A segment is simply a string part in the URL. We will use delete by ID and will return our response with no content status. For retrieving all tweets, we will define get. We will use the find method and the result will be the list of bson document, so we will convert them to tweet entity. Here is the code to start our server and shut down our server. Let's run our app and test it. I'll use Postman REST client to run our app. First, let's create a new tweet. Created. Now, let's get all tweets. Yeah, we only have one tweet. Let's test get one tweet by ID. Excellent. Let's delete this tweet. Yes, we don't have response body and our response status code is 204. Let's list all tweets. Yeah, now we don't have any tweets. We now successfully tested our logic app manually. In the next video, we will learn how to write a unit test for our app. See you there! Welcome to the last video in Section 8. Let's test our REST API. In the previous video, we implemented a REST API for Tweet resource. And using the Postman REST client, we successfully implemented our test API. In this video, we will take a look at how to write test cases for our REST API. Let's start. First, we will add the Akka HTTP test kit module and Scala test in our dependencies. Now, let's start writing our tests. We will implement 4 test cases to read, create, delete, and get a tweet. Here is the test class that extends flat spec, must matches, Scala test root test, before and after all, and REST API. The REST API trait contains our roots. And here is the implementation for the after all method. It will drop a collection from DB after all tests are finished. Now, let's start writing a test case for the read. First, let's create a tweet using the save method from Tweet Manager. The save method will return future of created, so we will wait for the actual result to get the ID for the created tweet. Now, let's send a GET request to our root and check the response. Our response's status must be equal to OK and should contain a list of tweet entity. So, we will convert the response to a list of tweet entities. This list must contain one element, and this element must be equal to our created tweet. Let's run our test. Great! Now, let's test creating a tweet. We will send a post request, which contains a tweet. The response's status must be the created status code. Let's run. Excellent! Now, let's test delete a tweet. We will create a tweet using Tweet Manager. And get the tweet ID from the result. Then, let's send a delete request to our roots, and the response's status code must be equal to no content status code. Let's run. Great! Now, let's write the last test for reading a specific tweet. First, let's create a tweet using Tweet Manager and get a tweet ID from the result. Second, let's send a GET request to our roots, and the response's status code must be equal to the OK status code, and the response must contain a tweet, so we will read the response as tweet entity, and this must be equal to our created tweet. Let's run. Excellent! Of course, these tests are happy tests, but I think now you can complete all tests for our REST API. We are introduced to the Akka HTTP module, and have discussed some topics on it, such as client API levels and server API levels. And we have implemented REST API, and finally, we are introduced to the Akka HTTP test kit module to test our REST API. See you in the last section on our Akka trip, Working with Common Patterns in Akka. Welcome to the last section on our trip, Working with Common Patterns in Akka. In the previous section, we have introduced Akka HTTP module, and we have worked with the client-side and server-side APIs, and also implemented REST API and test cases for it. In the last section of our course, we will take a look at some of the common patterns on Akka, such as balancing workload across nodes, throttling messages, shutdown patterns, ordered termination, and finally, scheduling periodic messages. Let's start with balancing workload across nodes in this first video. In this video, first, we will quickly go through balancing the dispatcher. Then, we will take an overview on the pattern. And finally, we will check the implementation. Let's revise the balancing dispatcher router, which we saw in one of the previous sections. Balancing router dispatches a message to an actor only when that actor would otherwise be idle. And of course, we remember all our actors shared with the mailbox. If we want to distribute work over remote actors, you can't use balancing dispatcher because every actor on each node has a different mailbox. So, if you want to use balance work with remote actors, you should use the work pulling pattern, which has been described first by Derek Wyatt. Let's take a quick overview before checking the implementation. We will have a master actor that will coordinate work, and have some of the workers that will execute the work, and these workers work on different nodes. The main goal is to implement the main fundamental concept of balancing dispatcher with remote actors. So, when the requester actor sends a message to our master, the master doesn't route this message immediately to any workers. The master will wait until one of the workers sends a request to work. So, let's assume worker 1 on node 1 finishes his work, and it will be idle. So it will send a message to the master to request a new work. The master will send a work to this worker. When worker 1 finishes this work, it will send work done intimation. This is the main idea of this pattern, but in order for the pattern to be valid, we must have concrete instances of the master on some node and the workers on the same node or other nodes. And when the worker starts working, it must identify itself to the master. So, each worker must know the location of his master, and the master must be running before the workers try to register with it. Now, let's check the basic implementation of this pattern. Here is the protocol between master and worker. These are the messages from a worker, worker created, worker request work, and work is done. And these are the messages from master to worker, work to be done, work is ready, and no work to be done. Here is the implementation of the master. We have workers variable that holds all workers and the work they may perform on it. And we have works queued that represents the received work. And here is the notify worker method that is responsible for sending work is ready message for each worker, if the master has work on the queue. Here is the implementation for receive. When master receives the worker created message, it should have a watch on the new worker and then add it to workers and call the notify workers method. When it receives the worker requests work message, it should check whether this worker is present on its workers. Then, if the work queue is empty, it will send no work to be done to this worker. But, if the work queue isn't empty and this worker doesn't have a work, it will dequeue a work from the work queue, assign this work for the worker, and send it to this worker. When it receives the work done, it will check whether this worker is present on its workers or not. If this worker doesn't exist, it will log, and if it contains on the workers, it will update the assigned work. When the receive has terminated, it will check whether the terminated worker has work or not. If it was working on something, the master will send this work for himself, and, then, the master will remove this worker and unwatch it. Anything else will add it on work queue and notify all workers. Here is the implementation of the worker. We implemented worker as an abstract class because we should implement the doWork method that executes the actual work. The worker takes the master path on the constructor, and here, to take actor ref for master from actor path. In the pre-start method, it will send worker created to the master. Our worker has two states, which are working and idle. In the working mode, we will ignore any message except work complete, which is sent by the worker itself when he finishes its work. When it is received, the worker will send work is done and worker request work to the master and switch itself to idle mode. In the idle mode, when the worker receives the work is ready message from the master, it will send worker request work to the master. And when the worker receives work to be done, we will call the doWork method and switch it to the working mode. If it receives no work to be done, we will ignore it. That is the basic implementation for this pattern. At the end of the video, we express balancing workload across node patterns. You can check all details for this pattern from here. See you in the next pattern, throttling messages. Welcome to the second video of the last section, throttling messages pattern. In the previous video, we saw how to balance our workload across nodes. We also discussed how to implement balancing dispatcher with remote actors. In this video, we will take a look at another pattern called throttling messages. We will take a quick overview on this pattern and then take a look at the implementation, and finally, we will use this pattern. Let's start. Sometimes in our application, we need to make HTTP requests to an external web service, and this service has some limitations. If we exceed the specific number of requests in a specific period, we will get a block or a need to pay. So, you need to make sure your application doesn't exceed this limitation. With the throttling message pattern, we will make sure the messages are not sent out at a high rate. The throttler will be based on a timer. This means, at every interval, the throttler will send a specific number of messages. For example, if you want to send 3 messages every second, the throttler will receive messages from you and will send exactly 3 messages each second. And if it receives more than 3 messages per second, it will enqueue them and send them in the next interval. Now, let's take a look at the pattern skeleton. Here is a skeleton of the time-based throttler. It is an FSM actor that has 2 states, idle and active. The data will contain the target actor, number of messages that got left in this period, and the queue of messages. Throttler will take a rate of messages on the constructor. It will start on the idle state with data that contains target as none. A number of left messages on this period will be a rate, and an empty queue. On the transaction from idle to active, we will set a timer, and from active to idle, we will cancel the timer. This timer will send a tick message at every duration from the rate. In the idle state, it will handle set rate, set target, and enqueue any other messages. When a set target message arrives and our queue is non-empty, we can start sending messages. When a set target message arrives and our queue is empty, we stay, recording the new target. When a queue message arrives and the target is not set, we stay in idle, after adding the new message to our queue. When a queue message arrives and the target is set, we jump to active, delivering the message that we just received. In the active state, it will handle set rate and set target like in the idle state. When a set target message arrives to unset the target, we jump to idle. With no target given, all we can do is queue messages. When a set target message arrives to change the target to another one, we update our internal state, D. When a queue message arrives and we have vouchers left, we use them. When we've run out of vouchers, we put the message at the end of our queue. Now, let's implement a simple example that uses throttling actor messages. This pattern is on the External Contribution subproject on Akka, and the recommended way to use something from this module is by copying the source code on your own code base and changing the package name. Because the Akka team does not restrict updates to this subproject, even during the otherwise binary compatible releases, and modules may be removed without deprecation warning. So, I just copied the timer-based throttler to our project. And now, let's define a simple actor. First, let's start to define our actor that receives messages from timer-based throttler. It's a simple actor. When it receives anything, it will print a message with the current time. Now, let's define our throttler instance. We will create props of timer-based throttler, and our rate will be 3 messages per second. Now, let's send our target to throttle, and, then, let's send 5 messages. Let's run. If you noticed, the first 3 messages are received in the first second, and the last 2 messages in the next second. We discussed the throttling message pattern in this video, and how to implement it. You can check full documentation from here. See you in the next video on shutdown patterns. Welcome to the 3rd video of Section 9, Shutdown Patterns. In the previous video, we worked with the throttling messages pattern. In this video, we will take a look at shutdown patterns. We will take a quick view on the pattern implementation. Let's start. I think you remember these lines from our examples. We always pause the main thread before we shut down our actor system to make sure our actor has finished. In Akka, you don't have a flag or configuration settings or callback you can register on to tell the actor system to terminate when everything's finished. This is because Akka is inherently asynchronous and does not internally know when done is, since there may be incoming messages in flight still. Now, what do you think finish means? Or how does Akka know your application is complete to shut down the actor system? Maybe the answer is when mailboxes of all actors on applications are empty. This sounds natural and logical, but this answer isn't correct because sometimes the mailbox is empty, but the actor is working or waiting for response from an external service or another actor. Okay, you might think that Akka is smart enough to know whether this actor is working or not. Hence, Akka doesn't shut down until the actor finishes processing the last message. But what will happen if the actor processes his message in the future? In my opinion, our application should be termed finished when it says I'm finished. We don't need Akka to guess whether it's finished. So, we should define the logic that tells Akka that we are done, and now it's safe to shut down the actor system. Derek Wyatt has designed a pattern to manage the shutdown process on your app. The main concept of this pattern is a Reaper actor. Reaper is an actor that watches other actors, and when all actors have died, Reaper will shut down the actor system. Now, let's take a look at the Reaper implementation. Here is the Reaper object that contains the Reaper name and case class that represents the Watch Me message. Here is the implementation of the Reaper. The Reaper contains an array buffer of actor ref that contains all the watched actors. And this actor handles two messages, Watch Me and Terminated. When Watch Me is received, it will watch the actor and then add it to watched array. When Terminated is received, it will remove the actor from the watched array and check whether watched array is empty. Then it will shut down the system. Here is the trait called Reaper Watched. When you implement a new actor and want the Reaper watches this actor, you should extend this trait. Now, let's implement a simple example. We have a target actor from the previous video. We will just extend the Reaper Watched traits. In the app object, let's add our actor system. Then we will create a running instance from the Reaper and a running instance from the target actor. Now, let's send any message to the target, and then the poison pill message to terminate the target actor. Let's run. Great! It's working, and our actor system shut down after the target actor finished. So the meaning of finished depends on your application, and you should define this meaning. At the end of the third video, we discussed the shutdown pattern, and you can check the pattern from here. See you in another pattern called ordered termination. Welcome to the fourth video in the last section, ordered termination. In the previous video, we introduced the shutdown pattern. We discussed that Akka should not guess whether your application is complete until it says I'm finished. It should depend on your application's logic. In this video, we will take a look at another pattern called ordered termination. We will take a quick overview on the pattern, then we will check the implementation, and finally, we will implement a simple app to use it. Let's start. When an actor stops, its children stop in an undefined order. Child termination is asynchronous and thus non-deterministic. If an actor has children that have ordered dependencies, then you might need to ensure a particular shutdown order of those children. This is the normal structure of a parent-child relationship. We have a master and some of the workers, and the master is responsible for managing its children. To be able to control the shutdown orders of children, we will change the normal structure of the parent-child structure. We will add the terminator actor. This actor will be responsible for managing the workers. The terminator will take the responsibility of terminating the workers from the master, and a terminator will watch the master. When the master dies, the terminator will execute the kill logic for the workers. Now, let's check the implementation for the master, worker, and the terminator. Let's start with the worker. It is a simple actor. When it receives any message, it will print a message on pre-start and post-stop methods. Now, let's check the master implementation. The master will take the terminator reference on the constructor and on pre-start will ask the terminator to get children. The master has two states, waiting and initialized. It will start with the waiting state, waiting for the terminator to send the children. In the waiting state, when it receives children, it will switch to the initialized state. In the initialized state, when it receives any message, it will print the message. Let's move to the terminator. Our terminator will take props of child and number of children on the constructor. In the pre-start method, we will create children t-children. The terminator has two states, waiting and children, and it will start on the waiting state until the master requests the children. In the waiting state, when it receives the get children message, it will watch the master and then send children to the master and switch the children to the given state. In the children's given state, when it receives get children, it will make sure whether the sender is an original master, and then it will send the children to the master. When it receives terminated, it will call the kill kids method. When received all dead, it will stop itself. the all dead message will be sent when all children die. Let's check the implementation of the killKids method. It is a function that takes a list of kids and returns future. It is a recursive function, and we use a graceful stop to terminate each child. Here is an order method that orders our children. Here is a simple implementation, for it just reverses the list. Now, let's try this pattern. Let's create a system actor, terminator, and master. Let's send a message and a poison pill. Let's run. Great! Our children terminate in the reverse order. In the end, we discussed ordered termination pattern, and you can check it from here. See you on the last video on our trip, Scheduling Periodic Messages. Welcome to the last video on our trip in Akka, Scheduling Periodic Messages. In the previous video, we introduced how to manage the order termination for the children actors. In this video, we will take a look at how to schedule periodic messages. Sometimes in our examples, we created a scheduler to schedule messages to an actor. In this video, we will schedule the message in two different ways. Let's start the implementation. In the first approach, we will schedule messages in the constructor of the actor and cancel it on the pre-post method. We will start sending the first message after 500 milliseconds, and then after every 1 second a message will be sent. Let's create a running instance on our app. And run the app. Great! Our actor receives a tick message after every second. In the next approach, the scheduled periodic message sent will be restarted with the actor on its restart. This means the time period that elapses between two tick messages during a restart may drift off based on when you restart. The scheduled message sent is relative to the time that the last message was sent and how long the initial delay is. The worst-case scenario is interval plus initial delay, and in this approach, you may fill up the mailbox with tick messages. In the second approach, we will schedule one message in the pre-start method. And when the actor receives the tick message, it will schedule other messages. And we will override a pre-restart method, so we don't call pre-start and schedule a new message. Now, let's create a running instance and run the app. Great! Our actor receives a tick message every second. In this approach, we won't fill up the mailbox with tick messages if the actor is under pressure, but only schedule a new tick message when we have seen the previous one. At the end of the last section, we have introduced some common patterns. In this section, in Akka, you can use them as follows: balancing workload across nodes, throttling messages, shutdown patterns, ordered termination, and scheduling periodic messages. At the end of our course, we have been introduced to and implemented a lot of topics on Akka, such as actors, actor structure on Akka, and hot swap actor behavior. And we covered some modules on Akka, such as Akka Persistence, Akka Cluster, Akka Test Kit, Akka Streams, and Akka HTTP. Hope you enjoyed. Goodbye!